I think it's on.
It's a great pleasure to have Pierre, and he will be talking about great escape and tunneling out of microstate geometries. And so over to Pierre.
Let's share my screen. Everyone can see it. It's okay.
Yep.
Yes. Yep, it's good.
Okay, so let's start. So first, thank you everyone for being connected, and thank you Yosif, Nick, and Laure Saubois for organizing the conference. It's a real pleasure for me to have the opportunity to talk. So the talk for the next hour will be about quasi-normal modes of asymptotically flat microstate geometries. So it's a third talk about such a topics. I hope you will not be annoyed. I think it's a good sign that now the fuzzball community starts to find some observables that we can get from microstate geometries and how it differs from black holes, which will be the crucial test for the validity of the proposal. So the result of which I will talk about are from a paper that we published in May with Yosif, Felicity, and Nick, with the usual Hollywoodian typic title of Saclay, The Great Escape, Tunneling Out of Microstate Geometries. So the outline of the talk will be the following. I will first discuss general motivation about studying quasi-normal modes. So about quasi-normal modes, astrophysics interest, and microstate geometries. Then in the second part of the talk, I will describe two types of microstate geometries that we have been able to compute spectrum of quasi-normal modes. So I will spend quite a bit of time going through these two first parts, which are preliminary, in order for everyone to understand well what are the background we are studying. And the main results come in the third part, where we compute the quasi-normal mode frequencies. And in the fourth part, I will discuss what it tells us about the energy and time decay in microstate geometries. Okay, so let's start by part one, the motivation. So let's start by the basis. What are quasi-normal modes? So quasi-normal modes are linear response of an object after perturbation. It encodes a lot of information about how an object relaxes. So we have a lot of manifestation of quasi-normal modes in everyday life. So I think the most famous one is in classical mechanics, when you play an instrument or ring a bell, you excite towers of sounds mode, which are quasi-normal modes, in a sense that they are labeled by an integer n here, and the time behavior is an exponential complex I omega t, where omega is a conjugate momentum along time. So the interesting property are essentially in the spectrum. We get omega n, which has a real part, which describes the normal frequency. So for the bell, it will be the harmonics of the bell, the chords that you can hear. And you have also a decay, an imaginary part, which give real argument in the exponential. So it's usually called decay rates. The sign of this imaginary part is crucial in a sense that it can be either decaying wave, if it's minus omega t, or growing wave if it's a positive number. So it really highlights directly some stability about the object. In astrophysics, we of course not interested in sounds mode, but more gravitational mode. So you can imagine to perturb a background like a black hole. So you perturb the metric and get some equation of motion from the Einstein equation for this small perturbation h mu nu. This will depend on everything about the background. So it will really encodes a lot of information about the background and also about the mode quantities like usual spherical harmonics, numbers, L and M. So this has been done for Schwarzschild initially like 70 years ago for the Schwarzschild metric by J. Riller. So what are the interests in quasi-normal mode in astrophysics? First, there is a very strong theoretical interest. As I said, like the decay rates, depending on this sign, can highlight linear instabilities in the sense that if it's positive or negative. It also suggests non-linear instabilities in the sense that if it's a really long-lived mode, so very small decay rates, the standard law is that it will, in GR, it's that it will form a black hole after a long time. So there are also a lot of suggestion from computing the spectrum of quasi-normal mode. There is also an experimental interest that the talk of Jose Morales and Bert Vaknook talked about that, in a sense that in the signal we get, gravitational wave signal we get from binaries, you have the last phase, a ring down phase, where you have only a remnant, which is highly excited. This remnant will relax through the channel of quasi-normal modes. So having an idea of what we should get at the vicinity of the object will help us to understand what kind of information we can get from this signal. So it should encode the resonances from structure at the vicinity of the horizon. It can be echoes, as has been mentioned by Bert, or also some shape modification, as it has been mentioned by Jose. Okay, so this is about quasi-normal modes. So there are a lot of topics in astrophysics for quasi-normal modes. As I said, there is a huge important question about stability, or black hole stability. So it has been started by Ridgey and Wheeler for the Schwarzschild metric, extended to Kerr later. You have also some tests of some modified gravity theories. So you take your best modified gravity by adding fields to GR or some corrections. You construct black hole background and try to see how the quasi-normal mode of the black hole are modified. There is also some ultra-compact stars object where quasi-normal modes have been computed. And now the question is, what about microstate geometries? So there are a few papers starting in 2004 where they try to really compute of a quasi-normal mode spectrum for asymptotically flat solution. And the main one about stabilities is Epron, Radial, and Santos in 2016, where they have been studying all the stability property of the microstate geometry through one type of microstate. The main problem with microstate geometry is you lose, I mean, for generic microstate, it can be very complicated structure. So you lose a lot of nice features of the background. You lose the separability of the wave equation. You lose a lot of symmetries. And then it's really non-trivial to find a type of microstate where computation is doable and generic enough to get kind of universal answer. So just a few words now about the microstate geometry program. So the goal of the program is to use some mechanism to construct objects that look like a black hole but support vast amount of horizon scale structure and make the space-time smooth at the horizon scale. Since quite many years now, we have a very large catalog of solutions corresponding to extremal supersymmetric 5-dimensional black hole. So all the talk, we will essentially focus on those types of black hole and microstates, in the sense that there will be 5D flat, extremal, and BPS. There are a few candidates of microstate geometries in 4D non-extremal, but because it's not a large catalog, now, I mean, the easiest is to focus on those kind of solutions. So the new paradigm of microstate geometry is really to replace the usual picture of the black hole in GR with an horizon, a throat, etc., with a smooth solution where down the throat, close to the horizon, you have a new phase of matter, which make the space-time to be smooth. So an essential ingredient that we will see in this talk is essentially the throat length of the geometry, which induce a huge redshift between the asymptotic time and the time in the cap. So we'll see that it will matter a lot for quasi-normal mode frequencies. So the question we'll ask is, what are the effects of the cap on the QNM quasi-normal mode frequencies? Is there any question? You can interrupt me anytime you want. If you want to ask question, feel free. So now I will describe the two kind of geometries of microstate geometry we will be using in this talk. So as I said before, we will try to describe 5-dimensional black hole, and we will place ourselves in 6D supergravity with two extra tensor methods. Why 6D? Because it's the frame, the microstate geometry are smooth. So symmetric solution is the following. We already see it in Daniel's talk. So the idea is you have a 4D base parameterized by the coordinate. My connection is working. Is it working?
Yeah, you seem to have lost your connection.
Can you hear me?
We didn't hear anything for the last 20 seconds, Pierre.
Okay, I'm very sorry. I think my connection is, it's Paris connection. It's pretty unstable. I'm sorry.
Can
There's
you
also an
back
option to call by phone, so you can actually call by phone, and if it doesn't work really bad, if it works really badly, you can also call by phone, and you can only see your screen, and we can hear you over the phone. It's also possible.
But okay, let's just back up to where you are now. That's great, and take it from there.
Okay, cool. Okay, sorry for this. So we will work in 6D supergravity, where microstate geometry are smooth, and try to describe 5-dimensionally flat black hole. So the ansatz for the metric for BPS supersymmetric solution is the following. It's something we have already seen in Daniel's talk. So you have a 4D base parameterized by the coordinate r, theta, phi, and psi. We will always assume that this base is flat in our case. And you have a 2-dimensional fiber where y is the extra S1 angle above our 5D flat space. And u and v are the null coordinates, c minus y, t plus y. And we normalize by square root of 2 because we like to have a lot of square root of 2 in our expressions. So this is a usual fiber. You defined some one form beta omega along v and u. And F and P are warp factors, which are electrically sourced. So just to get an overall profile of what you can have in those solutions, you have the easiest solution is maybe the BTZ black hole, fibered BTZ black hole, taking omega and beta to be trivial, and P and F sourced by 3 charge, Q1, Q5, QP. The full geometry can be decomposed in 2 parts. You have an F3 described by theta, phi, and psi of the base. And you have another 3-dimensional part, which is the BTZ black hole. It's asymptotically at the F3. And then when R goes to order QP and lower, you get an ADS2 times S1. At R equal to 0, we have the locus of the horizon. Now, the usual procedure to get asymptotically flat solution is to add some constant in P, in the warp factor. So adding such constant and an angular momentum for omega and beta, we get what we call the extremal D1, D5P black hole, which is asymptotically flat above, and then you have a BTZ times S3 throat. So we prefer usually to work with type 2B quantities, like the quantum number of the brane N1, N5, Np, and the quantized value of the angular momenta J right and J left. So the black hole is described by the fact that J left is identically 0. Okay, so this is a black hole we want to describe by constructing smooth geometries that look like such geometry above, close to the horizon. So the solution we will consider is a specific family of superstratum solutions. It's called the 2-1N supercharged superstratum. I will try to describe how it works very briefly. I mean, Daniel explained how it works in detail. So I will just give you an overall profile. So it's obtained by smoothly adding momentum to a 2-charge solution of radius A. So A gives the size of the cap. So the idea is you start with a 2-charge seed, where the distance to the supertube is given by sigma, and the component of the metric is pretty much the same as the black hole in the sense that you replace the r square by the distance to the supertube. F is identically 0 because you don't have momentum charge, and omega and beta have some angular momenta. So you can compute the conserved quantity. You have a QP, you have a J left and J right. And the regularity at the supertube locus required to fix the supergravity charge according to Ry and the radius of the supertube. The full geometry is an asymptotically flat supertube, where down the throat you have a global at the S3, so a smooth cap times S3. Now the procedure of superstratum is pretty much complicated, but the idea is you add momentum in a smooth way. So here for the 2-1N supercharged superstratum, we add essentially 2 parameters, a real number b and an integer n. So considering b very large compared to a, in a sense it really means that the a is the size of the cap and b is the size of the throat, you get a geometry which looks like the following. We make the transition now to the cap. We induce a very high redshift to the cap, and then the transition is made by a BTZ throat. So the metric component get modified by some b squared term, and this really induce a long throat between the flat region and the cap. So the full geometry really looks like a global at the S3 cap, a momentum wave here, which will source F, so which shows the momentum charge, and then a nice and beautiful BTZ throat, so black hole throat and flat space. So you can compute also the conserved quantities and the regularity condition, now also scale with B. So just to have an idea, if you take B very large compared to the side of the cap, A, you increase the charge here, and you keep J left to be small. So you can really approach the black hole regime, but keeping J left to be small means that you can smooth, you can have a smooth geometry at the close to the horizon. So the essential ingredient I was talking about, the redshift factor from the time, the boundary time and the time in the cap, is given for the geometry by n1 n5 over 2J left, which can be taken from 1 to its maximal value n1 n5 by choosing B according to A. A crucial point also is the presence of an evanescent ergo surface. So if you take R equals 0 and theta equal pi over 2, we have such an ergo surface. So the ergo surface is defined by the fact that the time-like killing vector, so dt, becomes null at this location. So it's a usual thing for black holes where we have ergosphere, where the time-like killing vector goes from time-like to space-like, but here it's evanescent in a sense that it goes from time-like to time-like, but in specific surface it becomes null. So we can imagine to avoid the usual instabilities of ergosphere, ergosurface for black holes, because it's evanescent, but it has been shown in the paper of Epran and Radial and Santos and followed by Kerr that you still have stable trapping at those locus for null geodesics. So those are the essential points that I want to make about the geometry. There is another type of solution we will describe, which is called the GMS solution for Giusto, Matur, and Saxena, which is obtained a bit similarly. You start with a two-charge supertube of radius A, and you induce a momentum charge by spectral flow. And the full geometry still look like a bit the supertube in a sense that it's flat space and a global at the S3 cap, but a huge redshift is induced by an orbifold singularity at r equal to 0. So the redshift is given by k, which is orbifold singularity now, and also given by n1 n5 over 2J left. But here, the redshift cannot be as big as for superstrata and necessarily bounded by n1 n5 power 1/4 if we want the supergravity approximation to remain valid. We have also in such a geometry an evanescent ergo surface. You can compute the conserved charge and the regularity, which is the same as the two-charge seed. So just to recap, what we will try to study is quasi-normal modes on top of some kind of typical microstates, the 2-1 and superstrata, which have essentially 3 regions, a flat space, a BTV throat, and a global ADI 3 cap. The redshift can be as big as n1 and 5. And we will also study some GMS solution, which is asymptotically flat, and global ADI 3 cap in the throat. So no black hole throat for those solutions. Is there any question? If you have, please feel free. So now I will discuss how to obtain quasi-normal mode frequencies on top of those solutions. So the usual procedure I was describing in the introduction was to perturb the metric and obtain the linear equations from the Einstein equation. It's usually a hard process when you have extra gauge field, as in 60 supergravity. So the usual procedure is to study scalar modes, massless scalar mode as the first ingredient, and maybe studying fermions, etc. But this usually mimic very well the profile you can get from perturbing the metric. So we will study minimally coupled scalar waves on top of our geometry, which can depend on 6 variables. Because our geometries have a lot of isometries, we can expand in Fourier mode along u, v, phi, and psi. So we choose omega, big omega, as a conjugate along u, the null coordinate q, qy, q phi, and q psi as a conjugate momentum along y, phi, and psi. Because there are circles, they are necessarily integrally valued. And now hr theta is our wave profile that we want to derive. So if you put this and that through the equation, you will get a wave equation, first with terms which are just second order and first order derivative along r and theta. and then a radial, separable pieces, only R dependent, separable pieces, which is only theta dependent, and an inseparable term. So usually it's really hard to compute anything when you have a second order equation with two variables. So you hope that you get the non-separable term to be identically zero. This is what happened for GMS solutions. They are simple enough to have a W equal to zero. So you can separate variable, define two wave profile, and radial one and an angular one, and get two wave equations, a radial one and an angular wave equation. So this lambda now.
Pierre, maybe just a quick question. Can you remind us which angle coordinate theta is exactly? Is it just you singled one of the S3 coordinates?
Yeah.
Or?
Yeah, it's exactly one of the S3 coordinates. Is like in our geometry, it's really describing. I mean, it's okay. It's this theta, which
okay, yeah.
Which essentially describe really like the S3 part of our 6D geometry, like this S3.
Yeah. Okay. Thank you.
Okay. So we get two equations. So one describing the S3 essentially, and one the radial a wave equation only along R. And we have this separability constant lambda, which corresponds to an effective mass. So even if we start with a massless wave equation from this 3D perspective here along the radial direction, we get an effective massive wave. So the goal is to solve those equations. The radial one, as usual, will encode all the quasi-normal mode physics. It will give the spectrum of quasi-normal mode, etc. Whereas the angular wave equation will give the quantization of this effective mass lambda. For the superstratum, unfortunately, for generic superstratum, you cannot get non-separable terms to be zero. So our choice of specific superstrata, the 2-1N superstrata, is made by the fact that you have the simplest kind of term non-separable pieces. Simplest in a sense that it's only proportional to omega square times something which is only depending on the background. And you can easily show that this value W compared to the omega square term in the separable potential is actually bounded by A square over the charge. So A square is the size of the cap, and here is the conserved charge. So in the black hole regime we are working, this is indeed a very small quantity. So the wave equation is almost separable, and you can do the similar job for that we have done for GMS. So you can separate variables and have two wave equations. Okay, so now for both families, we have two wave equations to solve. So we start with the angular wave equation to quantize the value of lambda. So for GMS and for superstratum, we have similar kind of potential. The important part are the two first term, which is in one sine square and one cos square. This is the usual spherical harmonic equation in S3. So you have two regular singular points at theta equals 0 and pi over 2. So the main problem, which makes the equation non-solvable, is those terms which are in cos square and sine square, or just cos square for superstratum, and we cannot solve the equation. But assuming that the coefficients are small, we have similar kind of quantization as in S3, and lambda scale like L times L plus 2, where L is integrally a positive integer. So assuming that the size of the bubble is way smaller than the radius of the Y circle, we can easily take lambda, which is equals to L times L plus 2. So now we will, from now on, we will really assume that condition to be able to compute anything. So now we want to solve the wave equation, which is the next step. So for that, we will convert to a Schrödinger equations. So we rescale the wave profile along R. We will choose a new coordinate X, where R goes from 0 to plus infinity. So
Pierre, question?
Yeah.
The radius of the Y circle, where is this? Far away or near the bubble?
It's far away, I think. It's still like, I mean, it's more like the periodicity of the Y circle. I mean, in the sense that it's 2 pi RY. I think it's far away.
It's at infinity, no?
Yeah, but I'm just wondering if there is some kind of factor in front like Q1, Q5. I think it's far away.
It's also the proper distance at infinity around the asymptotic Y circle.
Right.
Thank you.
So, okay, now we try to convert the equation through a usual Schrödinger equation by rescaling the wave profile and changing coordinates. So the origin now is at x goes to minus infinity, and the boundary is at x goes to plus infinity. So in both families of solution we are studying, we have an asymptotically flat region. For large x, it's a flat region, and in interior we have a weird but smooth solution. Smooth in a sense that the potential will be positive here, and we can have a classically allowed region. So let's discuss first the common point, which is a flat region. Taking x to be large, we recover the usual potentials that we get in asymptotically flat background. So we have first a damping factor. So at large x, you can see here the exponential 2x, which is a r square. So it's the usual damping factor in flat space. And a constant term here, which is given by the mass, the effective mass of the wave, and some extra correction from the gluing to flat space. So here you can really see that we already have some kind of bound on the quasi-normal mode frequencies, in a sense that if the damping factor is not negative, it will mean that the potential blows. You cannot have any oscillating wave there. So we don't have any quasi-normal mode. So this is the first condition. Omega times omega plus qi needs to be bigger than 0. In the other side, if we don't have the constant term there to be a positive plateau, it will be a negative plateau. So the wave will be perfectly reflective, and you don't have also any quasi-normal modes. So this is a condition of existence of quasi-normal modes for our solution. And we will usually take the low energy approximation, which consider omega times omega plus qi, very small compared to this quantity. In this approximation, the plateau here is given by its maximal value given by the mass, L times L plus 2. Why this approximation is because we're interested in very long-lived mode. So we want the biggest barrier possible. Now the boundary conditions that we constrain our wave for quasi-normal mode, I mean, it's the usual one, because it's smooth at the origin, we want some smoothness of the wave. So it means that the wave needs to be decaying here at x goes to minus infinity. And some oscillatory outgoing wave at the boundary here. So some right moving wave at x goes to plus infinity. And now the question is how to relate those both boundary conditions in the interior for our solution. Of course, this is not exactly solvable. So you need to find some new techniques like match asymptotic expansion and WKB approximation to get the constraint of relating those boundary condition and get the quasi-normal mode frequencies. So let's start by GMS backgrounds. So like the GMS backgrounds I was explaining in the first parts are just made of two regions, an asymptotically flat region and an AdS3 times S3 cap. So the potential now decomposed in two parts. You have first an AdS3 part in the interior and a flat part in the exterior. So the potential in the interior will be well described by the cap potential there. And in the exterior, it will be well defined by the flat potential as we thought. And the question is, because the barrier is large, you have a large overlapping region. So it's really tempting to take kind of asymptotic match expansions to solve those wave equation. So in the interior, the wave will behave as an usual AdS3 wave. So the wave profile will be given by the usual hypergeometric 2F1, which are smooth at the origin. In the exterior, you get the usual outgoing wave at the boundary. And then it will be some kind of linear combination of Bessel functions. Now the goal is to match them in the intermediate region, and you will get the constraint on the frequency omega. So it's usually hard to solve this constraint, but in the GMS papers, they show us how to solve it perturbatively. And what you will get is two towers of quasi-normal mode frequency, which is given by a first 0th order, omega n0, and a first order. So the 0th order is when the barrier is considered very big, so infinite, and you will recover the usual bound state of the cap. So here we can see that it's the usual bound state of AdS3 of the AdS3 cap. In a sense, that it's linearly spaced by this quantum number as a mod number n. And the k here is the redshift value, 1 over the redshift. So it gives the energy gap between successive modes. So really the 0th order of the quasi-normal modes is the usual normal modes only of the cap. Now you can get to the next leading order, and you will have a purely imaginary contribution to the spectrum. It will be very small in the sense that it's a perturbation. So it's pretty much complicated expression, but the important point is that it depends on the redshift factor, again, from the cap to the asymptotics, and the mass L. So the L comes here. It also comes in the 0th order expression. So the takeaway message is really you get a linear contribution, which is only the normal modes of the cap, and then a correction, a very slow decay rate, which give how the wave leak to infinity. So the first question we can address is the geometry linearly stable? So the wave profile behaves according to time as follows. We have the proper oscillation given by the normal frequencies of ADS3 of the cap. And then we have a decay part. We can actually show that for both towers of frequency given by the plus and minus, these terms always lead to a decaying wave. So our solutions are linearly stable for both branch of solutions. So this is everything about GMS that I want to say. Let's try now to see what do we get if we consider more typical geometries like superstrata. So here we cannot really apply a match asymptotic expansion technique in a sense that we have 3 regions, a flat one, a BTV throat, and a cap, ADS3 times S3 cap. So we can still apply asymptotic expansion in this between BTZ and flat space, but it's impossible to apply it from the cap to the BTZ region because we don't have an overlapping large region. So what we use is the usual WKB approximation, and we will get similarly a tower of frequencies labeled by the mod number n that we will treat perturbatively. There is an important point to make is to define some range of energy, in a sense that if we take very small energy, intuitively the wave will be localized down the throat. So this is really the case that we have here in this picture. If we take big N to be very small, so very small energy, the classically allowed region in the potential will be essentially supported in the cap region, so very down the throat. Any effect from the BTZ throat would be subleading in a sense that the term is already given by the mass term, is pretty much constant, so you don't care about any effect from the BTZ throat. It's quite intuitive picture in the sense that the wave will be localized here down the throat and will not explore the detail of the BTZ throat, and then are perfectly insensitive to this. And it will really look like some modes in a DS3 that are directly glued back to flat space. So this is the first regime of energy we have identified if we draw the mod number, so the energy level of the mode, and according to its mass, L. So for any L, you will have a tower of modes. At the beginning, it will be localized in the cap. And at one point, it will start to explore the throat here. So what does that mean from the point of view of the potential? It means that the classically allowed region will get deeper and start to leak on the BTZ region. So here you will have some modification from BTZ in a sense that it will not be given by the mass term. And here any modification will be sensitive. So this is what we call the intermediate energy regime, where the BTZ throat start to have an impact. So this is the main difference with GMS solution. The presence of the BTZ throat gives us 2 regimes of energy, one which is only sensitive to the cap and one which start explore the BTZ throat. You have also the upper bound of quasi-normal modes where no mode exists. Well, the result we add for superstratum geometry.
Pierre, just a question for the last slide. So this omega n, you get a correction which is only from the WKB matching. So this correction is going to be real, and then later on you're going to correct this further, coupling it to flat and get an imaginary piece. Is that what's going on?
We directly considered flat geometries.
Okay. So delta omega n would, as you presented before, is going to be imaginary.
We get an equation for the spectrum, which is hardly, it's very hard to solve it directly. So what you will do is essentially first assume that the barrier is really, really large, and you will get the first thing. And then the second order correction you will get is when it's very large, but finite. But
okay, yeah, thanks.
It's in flat space. Okay, so what we get as a result is similar as GMS. Like for both regime of energy, we get the first order in the spectrum of frequencies is given by, once again, the energy gap. So the normal frequencies of the cap. So the energy gap will be given by 1 over the redshift from the asymptotic flat space to the cap, which is equal to 2j left over n1 n5. So this is the usual, once again, normal frequency of the cap. And then we get the corrections, which also depends on the energy gap, so the redshift, and have some extra decoration in front, which is how it glues back to flat space. So the difference between the different energy regime will be essentially subleading, in a sense that for large L and large energy N, the decoration from the fact that it's exploring or not the BTC throat are really subleading there. And yeah, we'll give a different expression there if it's at lower energy regime or intermediate energy regime. So those expression of the spectrum we found, we really believe that it's a universal feature at low energy. The idea is really whatever non-separable microstate geometry you have, the very low energy regime will be only sensitive to the cap. It will be the normal frequency of the cap that directly glued back to flat space. So this seems something we really believe as a universal feature of microstate geometry with a long BTC throat. So this is a spectrum we'll get now. Let's try to extract some interesting physics about this. So the limit we will consider is called the Eikonal limit, which is a large L limit. So the large mass limit, let's say. It's a standard geometric optic limit where the wavefront follows the null geodesics of the particle. So it's the best way to recover the result about stably trapped time-like geodesics that have been found for microstate geometry. So we are also interested in trying to find the long-lived modes in our asymptotically flat solution. So let's try to get the large L limit in our geometries. So this is just a reminder of the spectrum, and we want to find the decay rate given by delta omega n for large L. So you can see that L enters directly in delta omega n, but also it enters indirectly through omega n0 here. And you have kind of different scaling of omega n0. It can either scale like hell, or it can either scale like a constant if you succeed to kill this L behavior by fixing what we had depending on our geometries, a function of qi, q5, cube psi. So we have shown that by fixing qi, q5, cube psi in the superstratum or in the GMS solutions, that if you kill the L behavior here in omega n0, so omega n starts to behave as a constant, the wave profile corresponds to waves that are highly peaked at the evanescent ego surface of our geometry. So you can really derive all the wave profile of the beast and see that it's really localized at r equals 0 and theta equal pi over 2 for the superstratum. So it's, I mean, kind of coincidence in the sense that we pick something where really that make a different scaling in L, and it perfectly corresponds to those evanescent ergo surface modes. For the specific choice, you can really see that the large L limit for the decay rates is very small, in a sense that you have an L factorial there, which makes it really, really low. And you have at leading order L power minus 2L. So it's a very small decay rate. At next leading order, you have once again the energy gap power sum 2L plus 3. So those are for the mode at the evanescent ergo surface. If you find a different choice of qi, q5 cube size, so any choice, omega n0 will now scale with L, and the decay rates you will not have anymore the L power minus 2L strong factor in front, and it will just scale as energy gap power 2L plus 3. So it's also a direct test of the strong property of an evanescent ergo surface. So the modes that really localized around the surface are very slowly decaying to flat space. So once again, it seems to be a universal behavior of a quasi-normal mode decay rate in microstate geometries with evanescent ergod surface. It's really the slowest decay rate you can find in such smooth geometries with this L power minus 2L. So now I will discuss what it tells us about energy decay and time decay in our solutions. So here we will really be specifying everything according to the quantum numbers of the mode. What we want to know now is really something independent on any excitation, in a sense that you perturb the background and try to see some very characteristic quantities that will show how the object relax. So we want to find a quantity that characterizing the background only. And for that, we will define.
Can I ask a question before you move on?
Yeah.
Can you say anything about the S wave, or is completely oblivious to the expansion that you're doing?
Yeah, I think it's pretty much. Yeah, I think. Yeah, I think it's pretty much inside the. Yeah, I mean, I don't have much to say.
Sorry, Ibu, when you say the S waves, are you talking about the fact that you may want to put the quantum number L to be a small number, like 0 or 1?
Yes. So how do I know those waves are? I mean, so this analysis tells me large L waves doesn't blow up this structure. What about the small L guys? Is there anything that could be said about them?
As I said at the beginning, any L, it's linearly stable in our geometries.
I think that the other thing also is that so the point is that the evanescent ergod surface, the locus of where the supertube was, is around the equator of the sphere. And so if you want to have something that localizes highly on the sphere, which means a high quantum number on the sphere, and these other quantum numbers, Q phi, Q psi, have to be chosen so you localize. It's like YLMs, and you're taking YLL, roughly speaking. That's the thing that localizes very, very sharply on the sphere and localizes on the evanescent ergod surface. And that's what gives you Pierre's middle expression. I think for generic L that's small, the energy is going to be exactly like his behavior for what's called generic modes. They're not going to be these things that localize. They're going to be spread all over the place. And therefore, their quasi-normal modes will just be this E gap to the 2L plus 3.
Yeah. But I think the question of Ibu was about stability at small L. But
yeah.
I mean, there is no problem. I mean, like the solution we have are all linearly stable. So like the wave doesn't blow for any L, whatever. So that the okay.
Sorry, one more question related to that, but that depends on the ratio of A over R. Can you say anything about if that number becomes order 1? Can you see some pole that could be generated?
What do you mean by R?
In omega n? A over R. Yeah, so you made an assumption that A over R was very, very small.
Yes.
So at small L, you might imagine you could do some sort of perturbation theory and to see whether there could be something that can happen with A over R such that this thing fails to be unstable. I
mean, from the expression here, it cannot be unstable. I mean, this coefficient there is necessarily positive and will necessarily lead to a decay, whatever you do. I mean, even if this is big, or I mean, like it's like the time behavior of the mode will be I delta omega n t, and so you will get minus this t. And so if it's positive, it's always decaying. After it can decay slowly or not slowly, but it's never blowing. That's what I mean. Whatever. I mean, even if you take A or RY, you're meaning that the result doesn't stand if you take A over RY small, a big.
Yeah, that's the question that I'm asking about, really. Is there anything what you could say about that? Maybe through some perturbation scheme.
I mean, the result will stand, but you will not have L here, but some kind of square root of lambda. So it's mostly the quantization of lambda, which will be a bit different, but the result will be the same. So I mean, like how those L arised, we used the fact that this is small in order to have lambda equals L times L plus 2, which is the usual quantization of S3. But if you don't have it, I mean, it's just like here, you will get some square root of lambda term in sense. So I mean, I don't expect anything special when you have different kind of assumption for. I mean, the way we assume thing was more to access a result, but it's pretty much universal. I mean, at least for supersymmetric solutions. Okay, so is there any question? No. So yeah, as I was saying, we want something which characterizes the full decay of our solution, which is perfectly independent of the mode quantities like L, M, etc. So for that, we define the first order energy, which is the integration along a time like hyper surface of the density, some density energy function. And we will try to find a characteristic function, GT, that gives how the energy decays, essentially. So you try to find some function GT, which is independent of the mode quantities, which gives the shape of the decay. It has been shown in Eikonal and Radial paper that you need to use, when you have trapping surfaces, so ergo surfaces, you need to use some second order energy that involves some second derivative of phi. And so the result you want to show is to find some function GT that bounds the decay according now to ET, the second order energy E2 at time equals 0. So it has been shown for ultra compact stars that you can find a constant which is only background dependent, where GT scale like log of t power minus 2. So it's still a very slow decay of the energy, but according to astrophysics, it's supposed to be valid and doesn't lead to any nonlinear instabilities. For the microstate geometry we have been studying, due to the present to the evanescent ergo surface, we have a very strong slow decay rate there. So by taking L as large as we want, it has been shown that you cannot find a function such a function that bounds that give a bound to the energy density, the energy function. So in Eikonal and Radial Santos papers, I have suggested that it will necessarily lead to a nonlinear instability in a sense that the decay is slower than log t power minus 2. So in our paper, we address a but to those arguments via 2 points. So the first point.
Can I ask, what is this E2?
Yeah, it's essentially, I mean, I think they add, I mean, here it's really sketchy, but they add some partial, I mean, they keep E1, but plus some second order derivative on phi. The full expression, I mean, it should be the same dimension, so you should have some factors in front, but I'm not really, I mean,
is this if and only if argument, or is this going only one direction?
Sorry?
Is this if and only if argument, or only goes one direction?
Which argument?
Don't find, for instance, if you don't find GFT of the right decay properties, does this mean there is linear instability? For instance, I can come up with some other E2 that has some other properties in different inequality.
It's not an if only if argument, in a sense that they it's more that the first order energy density is ill-defined if you have some kind of trapping surface. So they use this one, but I mean, also like the fact that this GT is something like a power law or log or blah, 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 which will lead to some nonlinear instabilities possibly, is also something very, I mean, it's not really well argued, in a sense that you need really to do the full back reaction things to know if it's really pathological to have such a GT.
There's a huge literature on this, on the subject of this log to the power 2 or log to the power 3 decay and ultra compact stars, which means things that can be as small as, up to about the Bookdale bound. Basically, the studies have shown that there are that these things usually have decays that are of order log t to some negative power, like 2 or 3. And so that's fairly well established. And what Eikonal, Santos, and Radial showed is that if you take this microstate geometry, that L to minus 2L, suggests that there is no such bound. In fact, the bound must be even slower than that. And so it doesn't prove there's an instability, but it says, you know, you're outside the usual realm of ultra compact stars, and therefore there may be something to worry about.
Yeah.
Can I make a comment as well?
Yeah.
What this, it's not an if-and-if statement, and what it basically states is that, so currently the ways most mathematical relativists would try to prove stability, they will need to find some bound on some energy quantity like E1 that will come from initial data. Here, if you just can't find such a GT, this basically tells you that you can't. It will be very hard for you using the current techniques that we have to show that the solution will be stable or unstable. But doesn't. It's suggestive of a nonlinear instability, but it in no way means that there will be one.
Yeah. Yeah, I mean, you really need to, if you really want to answer this question, you need to do the back reaction. It's really a complex problem. But I mean, it's really a suggestion, like, is there a nonlinear instabilities? But so in our paper, we address the question because the main problem is taking L to be very large. Like the problem of this factor is when L can be taken as large as you want. But in microstate geometry, I mean, the L arise at from the S3, which has a radius over the square Q1, Q5 power 1/4. So it's a fixed radius. Unlike compact star, we have really an understanding of how the L arise and how it will change the wave profile. So in a sense that the scalar wave profile will necessarily have L zeros on S3. So if you really derive the angular part of the wave function, it will oscillate L times around 0. So if you don't want to divide, the wave doesn't divide in some Planckian pieces the S3, you need to take L smaller than N1 N5 power 1/4. So in a sense, if you take L as large as you want, you will cross at one point this UV bound, and all the classical probe computation you have been using falls apart, and you need to consider some Striging modes, and you cannot trust anymore the spectrum we have derived. So everything for us is bounded in the sense that L needs to be smaller than this, and considering this fact, you can perfectly take the maximum value of L and show that you can get indeed a constant B, which is background independent, which is where the energy is bounded by the log of T power -2 as an ultra compact stars. We have shown also that the typical time decay, considering this L close to this larger bound, is something like the energy gap, so 1/3 the redshift of the geometry, power -2 L -3. So it can be a bit cheaty in the sense that we don't really know what's going on above this scale, in the sense that it's perfectly possible that the modes with large L also decay very, very slowly. But the standard law also, we use a second argument, which is about the standard law of the first Bolt proposal. So in GR, we assume that stable waves, so waves that are stably trapped for a very long time, at one point will back react and form a black holes. But following the first Bolt proposal perspective, we have other ingredients for us, a huge modularity space, which allows us to trust that the back reaction will not create a black hole, but create another first Bolt type of object, or in more current incarnation, in classical supergravity, microstate geometry. So the claim was, even if it's long-lived modes, they will form, the modes will back react and make a transition from a new from the microstate geometry we start with to a new microstate will be non-extremal and non-supersymmetric. So this is just a claim, but it's just following the new perspectives that the first Bolt proposal offer to us. So I will conclude here. So in the paper, we have extended preliminary work about quasi-normal modes of supersymmetric microstate geometries by considering now typical geometries that have a long black hole throat. We have shown that you have towers of linearly stable modes for which low energy modes are only determined by the cap. So you can really find that the quasi-normal mode spectrum is given by the normal modes of the cap and leak very slowly to flat space. So this is at low energy. We have shown that the extremely long durations that you can find when the modes are localized at the evanescent ergos surface is not an issue. And the final result is the time decay it will take for the modes to escape is over 1 over the redshift, so the energy gap, power minus 2L minus 3. So the outlook of this project is, can we compare those kind of computation, the time decay computation via some CFT computation on the D1, D5 CFT? Also, we would like to study bound states because we have, here we were restricted to quasi-normal modes that leak slowly to flat space, but on top of those solutions, you can perfectly construct some infinitely trapped solution in a sense. They are perfectly bound states and stay there forever. So it will be interesting to see how they behave in our microstate geometry. And then also, is it possible to address some linearity arguments and to find some transition from a microstate to another and consider those quasi-normal mode as an excitation of those transition? So I thank you for your attention, and I'm done.
Well, thank you, Pierre. That's great. Thank you. Any questions or comments?
Maybe a comment or question. I mean, I'm very surprised by your conclusion or proposal in the sense that usually I always thought in the first ball proposal that the idea was that the microstate geometry as solution were very unstable under classical perturbation, but it's a quantum effect that is meant to go toward other microstate superposition rather than a black hole. But I hardly imagine that classically you would not tend to form a black hole other than other microstates.
I mean, which kind of instability? A linear, non-linear? Like if you back react the mode?
I mean, non-linear, yeah, not necessarily linear, but small.
Yeah, I mean, nobody knows if it's unstable non-linearly. I mean, you can perfectly give a transition to another microstate, a non-BPS one. I mean, it's perfectly. I mean, it's a possibility in the sense that it will. You will excite your thing, and then it will transit to a non-BPS geometry, but maybe not a microstate geometry. So you don't have any kind of classical picture of it, but it can be a generic first ball, some kind of stringy structure. But I mean, it depends what you mean by instability. I mean, the microstate geometry will be unstable in the sense that you can lose the classical picture of the microstate geometry, but you can still.
All those solutions have evanescent ergo region, things like that, ergo surfaces and things like that, which tend to lead to instability. And also, if you form like, let's say you put a shell of matter and you let it collapse, you really expect to get the black hole. Not classically, I mean, not a microstate geometry. So you need the quantum effect anyway to resolve this. And I always thought the proposal.
I was saying before is like really in the I mean, like the microstate geometry are really covariant incarnation of first ball. So you don't expect to go from a microstate to another necessarily. Your question.
Perhaps it's simpler to reverse the perspective. The original proof that there was some issue of stable trapping near the evanescent ergosphere requires that you look at a very, very high value of L to see the long trap modes. And what this shows is that that value of L that you need to go to is hugely large, and therefore whatever the supergravity excitation that you're looking at is way sub-Planckian. So the supergravity analysis that is being used to show that there are these ultra long trap modes is way beyond its realm of validity. So nothing has been shown about ultra long trapping. Now, it's possible that there are stringy states that sit there for a long period of time, but no calculation has ever been done that inside its realm of validity that shows that there's ultra long trapping. Everything that's inside the realm of supergravity has this log t to the -2 bound. So the Eikonal Santos Radial calculation, when done in a microstate geometry, the value of L you have to take is where it leads to oscillations that are incredibly subplanckian. So even putting the law of superfusible proposal aside, that means, you know, the calculation simply has nothing to say about a real microstate geometry.
Yeah, I think this notion of stably trapped modes sort of accumulating on the evanescent ergo surface is a red herring. Well, maybe we should wait for my talk, but basically the thing can't be nonlinearly unstable in the sense of like, you know, an accelerated runaway, because the thing's living on the BPS bound. So at best, what you're going to do is you're going to start wandering the solution space. And so, you know, nonlinear, if you want to replace a pejorative like nonlinearly unstable to a statement that the system is neutrally stable and has a moduli space of BPS solutions, all you're doing is you're starting to wander into the rest of the state space of BPS solutions. And the rate at which you wander is going to be governed by how much energy you have above extremality. So, you know, the system can't run away because it doesn't have enough energy above BPS to run away. It'll just slowly start diffusing across the BPS configuration space.
I mean, could it be that you diffuse in BPS configuration space, but the gap to non-BPS states or to different states becomes smaller in some regions, and that's...
I think the gap is 1 over n 5. I don't think the gap can be... Generically, all the geometries, I mean, you expect from the CFT the gap to be 1 over n 5, and not neither bigger nor smaller. Because in the CFT, it's a long string of length n 5. So the gaps are always, the gap about the BPS is always 1 over n 5, and then you have a whole tower.
Well, that's a free film picture. I think that's a fairly naive picture. I mean, for example, in the SYK model, the gaps are exponentially small.
But that's because it's non-BPS, and I mean, in the bulk, in the geometries we built, you can see that 1 over n 5 comes out to be the natural value.
No, but even in BPS states, in BPS cases, so cases with, let's say, n equal to 1 supersymmetry or n equal to 2 supersymmetric SYK model, well, in that case, it depends on the precise value of the charge. In some cases, the gap is what you say, but in some other cases, it can be exponentially small. So it's not clear. I mean, I think it would be interesting to have a solid argument for what the gap is.
Yeah, I think a very small gap can form, well, that's more or less the theme of what I'm going to talk about.
Small in what sense? Exponential minus n1 n 5, or?
Well, in the sense that stringy degrees of freedom start to take over the dynamics.
I think that's exactly, I think, the broader point. It doesn't really matter what the gap is. The point is the Eperon, Santos, Real, and the related calculations only see ultra long trapping when they've done a calculation that's way beyond the validity of supergravity. So absolutely, when something falls in, it's ultimately going to scramble into stringy degrees of freedom. And how many it scrambles into depends on the gap. But the point is the calculations don't show nonlinear instability. I think what's going to happen is you're just going to start creating excitations around the state that is just some pile of fuzz around the supergravity background.
I mean, look, so the longest modes, the modes that, look, the system is built on all these solutions are built on supertubes. Supertubes have a huge moduli space of deformations. So I think in sort of the collective coordinate, approximation, which is supergravity, you can have arbitrarily slow motion on the moduli space And so you can make, wave packets, if you like, that are moving arbitrarily slowly on that moduli space. So in that sense, the gap is 0.
Are you assuming the moduli space is non-compact?
Well, I'm assuming we're working in a supergravity approximation where.
But then it's infinite, because in the supergravity, the dimension of the moduli space is n1 times n5. So essentially the moduli space has dimension n1 and 5. So then in the supergravity approximation you make the dimension infinity. I think Juan's question is, if you have n1 and 5 moduli space, the volume of the moduli space, as was computed, in Lunimatur and Lunimal Maus, is e to the power n1 times n5 square root with the 2 pi square root of 2 in front. So the volume is finite, the dimension is finite. So I think the space is compact. As in answer to Jan's question.
But this finite volume would give an exponentially small gap, right? I mean, if you have quantum mechanics on a finite volume space, you would have a...
Yes, but the dimension is very high as well. So I think for supertubes, we know that the gap is always 1 over n1 and 5. I don't think for supertubes you can get any smaller gaps, even in the two-charge system. Because I think there the gap is protected, if I remember right. And then, it was computed it can be computed both in the CFT and by doing some coupling of the D1E5 system with an outside source. This was done by Lunimatur and I think.
So what happens when you go away from extremality, you break BPS? That's presumed that the gap should become exponentially small.
No. So there's a question, given one particular solution, the gap to go from BPS to the next excitation, at least in the supertube case, is 1 over n1 and 5. Then you have more excitations, and on top of every supertube configuration, you can have one tower. The towers are not equally spaced. This was found by Nick and by Pierre and by other people, and by David Thornton and I and Pierre. If you compute the mass gaps, you find that various microstate geometries, the first one is 1 over n1 and 5. The next one can be like, 3.7 over n1 and 5. And then, it goes in steps of 3.7. The other one goes in steps of 4.9. So if you compute the gap between a random member of the tower number 5 and the random member of another tower, you will get exponential suppress. But it doesn't mean that you have to pay that small of an energy to go from one to the other, because they may be in different they may be very far away in the moduli space.
Okay, are there any more questions or comments or any?
I would just want to clarify, just a clarification question that I want to ask. So is it, if I insist to stay in the supergravity approximation, is it like as soon as I crank up L, then some stringy degrees of freedom take over and I transition to another state? But if I insist to model this in supergravity, then is the new microstate that I'm going to get, say it's coherent, most likely it wouldn't be, but say it's coherent, would it have lower L? In a way, within supergravity, how am I shredding L away? Does anyone has the comment on this?
Yeah, maybe so. So you can understand this, the instability that Eperon, Real, and Santos studied in a sort of a snapshot situation where you have an equibox axial shock wave in this geometry, and there's exact solutions to that. And so there's a parameter in the shock wave that is related to this to parameter L, and it takes you from more atypical solutions to more typical ones. And then once you reach the value where you have square root n1 and 5, which is the angular momentum of the typical microstate solution, then supergravity really breaks down. And you can then, and this process can be sort of understood as an entropic driving from atypical to typical states. And then once you hit that scale, supergravity breaks down, and the evanescent ergo surface should develop some string scale structure. But this is for the situation where you have this small microstates for the small black hole. I'm wondering if any kind of similar analysis for such an instability has been done for more D1, D5P, and if a similar interpretation can be given for that.
I don't think we know. We don't know what the typical states are in the D1E5P. So maybe the typical states are stringy, in which case the same will happen. But if the typical states are described by supergravity or Hilbert space of typical states can be spanned by supergravity solutions, which are smooth, then the answer is they don't need to become stringy. I think it depends on how the typical states will look. Some people believe they're going to be all stringy and so on, but maybe they're not. At least all the arguments people have used to argue the 3-charge microstates have to be stringy, all of them will have counter arguments against. So.
But anyway, at some point, whatever you drop into this thing is going to become some kind of scrambled into stringy excitations about some geometry initially, and then perhaps not. That geometric interpretation will ultimately disappear into some fuzzball. But at least at the level we're doing here, which is you drop in a probe and then maybe you backreact the probe a little bit, it will scramble into some excitations around this background. And the comment here is the ones that you want to say live a very long time are intrinsically stringy modes, so all bets are off in terms of supergravity analysis. Any more questions? Comments?
I have one. I was wondering if from this you can also see how this is different from the corresponding black hole. So for instance, in a time signal, etc., because you cannot immediately compare quasi-normal modes because they can be very different.
Yeah, I mean, it depends on this. I mean, it's not a response function we are computing, but in the sense that if you perturb, if you send a wave, we don't really send a wave into our geometries. In the sense that if you imagine that you perturb what would be the black hole and try to see how the response it will take, so how the details you can get from the cap, we don't really compute that. So. But the quasi-normal modes of the black hole is completely different. I mean, there is no good thing in the sense that you don't have any E-gap term. So it just really kind of suggests that if you perturb far away from the black hole, you send something. Here you will get an answer compared to 0 if it was a black hole. I mean, you will get some kind of echo, which is given by this time decay.
Okay.
But for the shape of how it, if you imagine the shape of the gravitational wave and stuff, this is more subtle, I think.
Thanks.
Just a sort of more generic comment. What are we looking at here? You're looking at some small oscillation down the bottom of the microstate geometry. You may be able to get some estimate of how long it takes for that to leak out, and maybe this is some incredibly infinitesimal temperature version of Hawking radiation, and maybe you can get some estimation from this decay rate about such a process. I've no idea. I haven't thought much further about it. But this is more likely to be about the decay of a fuzzball excited state than it is to be about something you could see with LIGO or whatever. Any more questions? Comments? Okay, then perhaps we'll resume in about 10 minutes for Emil's talk. And
we'll keep the recording going on YouTube,
yeah,
so that we don't have to get another number. So we'll keep the recording going. So we'll just mute all the microphones so that YouTube doesn't.
But if people want to keep talking, that's also fine.
Actually, no, because everything is going to go on YouTube. So if people are going to keep talking, we can actually stop. I mean, if people want to have a private conversation, maybe we can do it afterwards, because it's only 10 minutes. So.
Okay.
We can stand 10 minutes without.
Maybe I can share my screen.
I just muted everybody. Hosts and co-hosts can unmute themselves.
Emil, do you want to put your video on too so we can see you when you're not, even though we just have a big E. Ah, great. Okay, so we'll resume in about 10 minutes or so.
All right.
Coming back together.
All right.
Are you going to record it?
Sorry? Thank you for reminding me. Yeah, I will start it.
You're recording?
Yep, for posterity.
Right.
It's going on YouTube anyway for posterity, so.
Give it a couple of minutes. Yeah, it's still not quite time.
I just muted everybody. I just allowed everybody to unmute themselves for the talk. So, Emil, you should unmute your microphone.
Indeed. Now it has been unmuted.
Yep. So this is just allowing people to. So normally you have to mute everybody and then you have to mute them again in order to change the muting preferences.
Of course, of course. Okay, so
Yes, being 4 p.m., we should start again. So thank you for everybody for coming. And now it's Emil's turn, and he will be talking about stringy structure at the BPS bound. Over to you, sir.
All right. Thanks to the organizers for giving me the opportunity to speak. I only wish I was giving the talk in Paris. So the work I'd like to describe today has been building over the last few years, beginning with a paper with Stefano Masai, joined subsequently with David Turton in what has been a very fruitful collaboration. So what I'd like to describe today is an attempt to understand some stringy effects in microstate geometries, or more generally, stringy state structure for the BPS, at the BPS bound in the 1-brane, 5-brane system. So the BPS states that we'll be interested in are 2-charge microstates. And the first thing we'll do is to describe their geometry. The generic state of this form is called the supertube, and we'll describe its structure. And then for a very particular supertube shape, namely a round source configuration, we'll be able to develop an exactly solvable worldsheet conformal field theory models, and then discuss some of its stringy aspects. In particular, there's a very useful duality. It's a duality of the worldsheet conformal field theory called FZZ duality that will lead us to a stringy description of general supertubes. That then will allow us to discuss stringy features of the near source configurations and enable us to understand where singularities might be lurking in the half BPS configuration space, and give us, I think, some hints as to what is the relation between microstate geometries, their stringy extensions, and more generic fuzzball states. And in the end, I'll try to end with some speculations on the process of black hole formation near the BPS bound, for which you see an artist's rendering at the bottom of the slide. First question I should answer is, well, why NS5 branes? Why this particular corner of ADS CFT duality or gauge gravity duality? And well, we're interested in developing, looking at stringy effects. And so worldsheet string theory in the presence of remote backgrounds, and so in particular, almost all the examples of gauge gravity duality that involve deep branes is just a huge technical headache. And so we'll be interested in backgrounds which are sourced by only NS fluxes. And so that restricts us to NS5 branes, fundamental strings, and momentum as background charges. Now, NS5 branes are closed string solitons, so they're heavy objects whose effect on the background comes with strength 1 over G string squared. So their back reaction and the geometry they source have to be incorporated from the beginning into the worldsheet theory. So in a sense, this gives us a bulk description where lots of the gravitational effects that we're interested in studying are not things that are absent, they're built in from the beginning. Furthermore, the 1 brane, 5 brane momentum system is certainly a central example of gauge gravity duality. If we take the decoupling limit, taking the asymptotic value of G string to 0, then you get a linear dilettante throat associated to what's called little string theory. And then you can take a further decoupling limit where the radius of the circle that the 1 branes are wrapped on gets large. And if you take it to be going to infinity, that leads to an ADS3 limit and the standard ADS3 CFT2 duality. So the worldsheet formalism, we'll be able to see much of the structure. We'll be able to identify what states we're looking at in the space-time CFT and a lot of the transitions that are generated between various states in the space-time CFT. At the same time, we have our hands explicitly on the bulk space-time on the gravity side of the duality and its stringy extensions. So what are the class of states we're interested in? They're called supertubes. Basically, any 2 of the 3 charges, NS5, F1, we can construct a large collection of half BPS states. The particular BPS states we'll be interested in initially are those that carry NS5 branes and momenta. Eventually, we'll be interested in NS5, F1. Those 2 are related by T duality on the circle that the momentum is along. So because we have our hands on the exact worldsheet theory, that T duality is just a trivial relabeling of the data of the CFT. So we start with a stack of 5 branes. We're interested in binding momentum quanta to it. Well, what is momenta bound to a 5 brane? It's just waves on the 5 brane. In order to be BPS, all the waves have to be traveling in the same direction. So we'll put them along a circle, which we'll parameterize by a coordinate y tilde, because it's T dual to the circle that we'll be eventually interested in. There are, of course, a bunch of modes on the 5 brane. The 5 brane has a 2-0 tensor multiple living on it if we're in type 2A, say. And so there'll be 4 scalars which parameterize excitations of the 5 brane in the transverse space parameterized by x1 to x4. And so I've just depicted here as a function of y tilde, those wiggles in the transverse space. And I've color-coded the various 5 branes in the stack for you. We'll also be interested in putting a twisted boundary condition, which wraps as we go from y equals 0 to 2 pi ry. 5 brane 1 goes to 5 brane 2, goes to 5 brane 3, so that the 5 branes are all wrapped together into a single 5 brane that winds the y tilde circle and 5 times. So the general BPS wave on such a stack of 5 branes has n sub k excitations in polarization I. There are 8 bosonic and 8 fermionic polarizations. If we look at just the bosonic excitations, there are the 4 transverse scalars. There are 4 internal modes, NS5 tensor gauge field and a scalar. These are Ramond excitations. So these are the things we'll be turning off to avoid the headaches of Ramond fields in the worldsheet. So the counting of these states involves choosing a partition of N5, NP. So the total mode number adds up to some capital N, but then we can partition that into the modes in any way we like. And so the entropy of these things was counted long ago to be 2 pi square root of 2n5 np. And if you give the system some angular momentum in the transverse space, that subtracts from the available choices. The phase diagram, if you're thinking about this in the ADS3 limit, is that there's some threshold, some parabolic threshold above which the BTZ black hole entropy applies. You have a geometric horizon in the low energy supergravity theory. But then below what you might call the cosmic censorship bound for extremal black holes, there are further states in the theory. The 2 charge states we're dealing with live on the red line up to some maximum angular momentum of order N1, N5. So this NS5P duality frame describes a fibrane that's carrying momentum and is wiggling around in its transverse space. If we T-dualize that, then we will find the NS5 F1 supertubes, still labeled now. The momentum quanta have been turned into one brane winding quanta, and the states are still described by the same partition of now N5, N1. Now, the T-duality does something interesting. Because the fibrane now lies at an angle in general with respect to the direction that you're T-dualizing, the duality of NS5 branes is a mixture of duality parallel of a direction that's partly parallel and partly transverse to the fibrane world volume. Now, if I T-dualize along a direction that's parallel to a fibrane, it stays an NS5 brane. But if I T-dualize along a direction that's transverse, an S5 brane turns into a KK monopole. And a KK monopole in supergravity is a completely non-singular geometry. So what happens is that when you go to the NS5 F1 duality frame, the supertube becomes a KK monopole core, which extends along some wiggly contour. The geometry now becomes completely smooth, and the branes have become flux in the standard way that we're used to in gauge gravity duality. In some way, in some sense, the branes have somehow dissolved into flux, and where they are is a bit hidden. However, since the worldsheet theory knows about T-duality exactly, it still knows where the fibranes are in a very precise way in the T-dual coordinate. So what's the class of geometries we get after this T-duality? They were enumerated by Lunan and Matur, and follow-up work by Skandaris, Kanachiter, and Taylor. So as you've seen in a couple of talks already, the talk by Daniel Meyerson and the previous talk by Pierre Heidmann, the entire geometry is specified in terms of some collection of harmonic functions and harmonic forms. And the 2-charge geometries look like this. There's a harmonic function that's basically related to the fibrane source, harmonic function that's related to the one brane sources, and then some harmonic forms that go along for the ride. There's a dilaton, which is fixed in the near horizon limit to be related to the ratio of the one brane and fibrane charges. And there's an ambient B field because we have fibranes and fundamental strings sourcing magnetic and electric H flux. So what the Luna and Matur did was they gave a prescription, if you like, for what these harmonic functions and forms are in terms of some Green's function integrals. So we have 4 transverse dimensions. The Green's function goes like 1 over r squared. And if our fibranes are distributed uniformly along some contour f of v, then this is just the natural harmonic function for scalar harmonic function for such a source. The expression for the one-brane harmonic function you understand in terms of T-duality. This is just the stress energy tensor of momentum waves along the fibrane. And then this particular way of combining those harmonic functions into the geometry is obtained from the NS5P solution by using the standard rules of T-duality. And I should say that the nonlinear sigma model on this background is an exact conformal field theory because there's enough structure of supersymmetry and the killing vector structure of the background spacetime. So this geometry has 2 null killing vectors, namely that generate translations along the null directions u and v in the target geometry. They'll play an important role in what we're about to do. What I'm about to do is accumulate a set of observations and known facts about string theory on this background. So I hope you'll bear with me as I develop those facts. In the end of the day, they'll all get pulled together into kind of a coherent picture of what the microstates are near the BPS bound. But for the meantime, I just have to slog through a whole set of things about worldsheet conformal field theory and Westsamino-Witten models. And so I hope you'll bear with me as we develop the set of tools, which I think is probably incumbent upon me because not all of you are experts in worldsheet conformal field theory. So anyway, the first observation is that if I have a background that looks like this, and I make a nonlinear sigma model describing strings on this background, I can choose to gauge the isometries corresponding to translations in U and V. So, translations in U and V are global symmetries of the sigma model action. So I can gauge those symmetries. If I do so, there'll be terms linear and quadratic in the gauge field. The gauge field just appears algebraically, and I can integrate it out. And so I should say, by the way, that the gauge currents associated to those symmetries are, because of the structure of the metric in the B field, translations in V are purely holomorphic on the worldsheet. Translations in U are purely anti-holomorphic on the worldsheet. And so when I integrate out the gauge field, what do I get? I get J bar over sigma that looks exactly like the thing I have in the metric to begin with. And in fact, those 2 contributions, the original background geometry together with its correction that I get from integrating out the gauge field, exactly cancel one another. And so integrating out AA bar just eliminates this part of the metric and leaves a transverse geometry. So there's a very tight, and what is that that geometry? It's just the geometry of a bunch of fibranes separated on the Coulomb branch along the contour F that we started with in the Luna-Matur geometry. So there's a very close connection between Coulomb branch configurations of fibranes and Luna-Matur geometries, which are the half BPS states of the one-brane fibrane system. So that's fact number 1. And so next fact is that while it might be hard to solve the worldsheet conformal field theory for the generic supertube configuration, the particular case where the contour is nice and symmetric, namely a circle in a 2-dimensional plane inside the 4 transverse dimensions, is exactly solvable. And so the Coulomb branch geometry was understood by Givon and Kutuzov in a long series of papers starting a little over 20 years ago. The associated Luna-Matur geometry for the fibranes smoothly distributed in a circular array is global ADS3 cross S3. So this theory on the worldsheet is exactly solvable because ADS3 is just the SL2R group manifold, S3 is the SU2 manifold, and they both have H fluxes through them corresponding to the electric and magnetic string and fibrane sources, both at level N5. And so we have an exactly solvable worldsheet theory describing this Coulomb branch configuration of fibranes. So the worldsheet theory is the following gauged Wess-Zumino-Witten model. There's the part that's describing the transfer space of the fibranes, namely SL2R times SU2, of which you've gauged a U1 cross U1 to project this down to the 4 transverse dimensions. And then there are the longitudinal directions of the Coulomb branch fibranes, T, Y, and T4. We'll choose to completely compactify the fibrane world volume. So, basically the Coulomb branch array starts with a 10 plus 2-dimensional geometry. Gauge projects it down to the standard 9 plus 1 by choosing the gauge subgroup to lie entirely within SL2 times SU2. We'll note that this particular combination of currents indeed is a null direction in the target space because we picked the compact generator of SL2. It has equal and at level N5 has an equal and opposite killing norm to the current, any current in SU2. So these are 2 null currents, and gauging those null currents does exactly what we want. And with the nice benefit that all the quantities, all the harmonic forms and functions that describe this particular background geometry are given by group invariant quantities. So for instance, the 1 forms in the Lunin-Matur solution are given by the left and right invariant 1 forms on SU2. The coefficient of AA bar in the sigma model action is just the inner product of those 2 pulled back 1 forms. And so the harmonic functions, then when you eliminate the gauge field, you get 1 over the coefficient of AA bar. The harmonic functions just get naturally generated by the process of integrating up the gauge field. So you get the transverse geometry of the fibranes, not described in the natural Cartesian coordinates for the transverse R4, but in some rather funky looking coordinates until you get used to them. You start with the SL2R times SU2 Euler angles. These are just the usual global coordinates on ADS3 and standard round 3-sphere coordinates. And the way they package themselves into coordinates on the transverse R4 are what are called spherical bipolar coordinates. So x1 plus ix2 is this particular linear combination product of the Euler angle coordinates on the group manifold, and similarly for x3 and x4. And notice that the place where the harmonic function goes singular and you have a fibrane source pole is where rho equals 0 and theta equals pi over 2. And that's exactly the circle of radius A in the R4, just expressed in these peculiar coordinates. Okay, so time for next fact about this system. And that's something that's been known for quite a while, that these conformal field theories that you get by gauging a U1 on SL2 and SU2 have an exact worldsheet strong weak coupling duality. In the case of the SL2 mod U1 coset, it's to n equals 2 Liouville theory. This was something that was discovered by Fateev, Zamolodchikov, and Zamolodchikov, and in an unpublished work, subsequently brought to light by Givon and Kutuzov in their discussion of scaling limits, what they call the double scaling limit of little string theory. The SU2 mod U1 duality is even older. It's known that it's dual to what's called an n=2 Landau-Ginzburg model. This is just an n=2 theory with a free kinetic term and a polynomial superpotential z to the n5. Okay, and what will be interesting for our purposes is that basically there's an exact worldsheet duality that says that this space-time geometry that describes the transverse space to a bunch of fibranes is quantum equivalent to a worldsheet theory which just has superpotentials, an exponential superpotential for the Liouville part and a polynomial potential for the Landau-Ginzburg part. And that linear combination of superpotentials from the two factors factorizes into a bunch of monomial factors whose zeros, so the zeros of the superpotential are at the n-5th roots of unity. So you can read off where the fibranes are from the Landau-Ginzburg picture just by asking where are the zeros of the Landau-Ginzburg superpotential. And this parameter lambda naught is related to the parameter A of the geometrical description. Now, that FZZ duality is something that I should check and see if I have time for. Probably not. Let me just say, okay, well, let me just go through it briefly. So there are classical solutions of the Wessamino-Witten model. These are strings propagating in a group manifold. They factorize as classical solutions between the left movers and the right movers, very similar to free field theory. The highest weight states describe geodesics semi-classically that are just propagating up the middle of ADS3. If I say, look at the SL2R Wessamino-Witten model. And I can look at zero mode descendants, which are just strings that are oscillating around in ADS3 in some coherent fashion. There's an operation of the worldsheet theory called spectral flow, which basically takes one of these oscillating zero mode solutions and spins it up in the azimuthal direction, in the angular direction of ADS3. So that describes a string which is undergoing some kind of breathing oscillation as it propagates up in the time direction. And what's interesting is that, okay, here's the specific G of Z times G of Z bar that describes that classical motion. You can see it's all exponentials of zero mode elements of the current algebra. But there's an alternative description of such a breathing oscillation, which is that this is just some coherent oscillation of the first oscillator excitation of the string. And so I can also write something which is an exponentiation of Lie algebra elements where I'm exciting the first oscillator mode of the string. And it turns out if you just evaluate these exponentials and take the product and figure out what element G of Z and Z bar do I have, it's the same if I pick these particular parameterizations. So there's a statement that something which is only a zero mode excitation is simultaneously a coherent excitation of the first oscillator mode. And a particular case of that, since string oscillator mode excitations describe stringy states, is that a graviton, which is something which has the first oscillator mode excited once, is simultaneously describable as something which just has zero mode winding excitations. So this FZZ duality semi-classically is just a statement that the parameterization of the loop group has some redundancy to it, which sets up an equivalence between winding strings, which only have zero, what you might call winding tachyons, to gravitons and their relatives. So coming to a conclusion on this description of the Coulomb branch of fibranes, you might have thought, if you're a supergravity person, that the Coulomb branch of fibranes is something where if you go far away, all the sources kind of merge together and you're describing the linear dilaton throat of N5 fibranes. And that as you get closer to the source, you start resolving individual fibranes around the circle. And so the one big throat of N5 fibranes would devolve into N5 little throats of the individual fibranes. That's not true. And the geometrical picture breaks down near the source and gets replaced by this Landau-Ginzburg picture, which keeps track in a very stringy way about where the fibranes are through the zeros of the superpotential. So there's some kind of winding tachyon condensate, which is growing exponentially as you go down the throat. And the throat is growing linearly as you run down the fibrane throat. And so if this picture were correct, you would worry that you could just keep running down the throat, down into some little throat and reach a region of strong coupling. But that's not true. The world sheet theory saves you and says that no, secretly there's an exponential wall that keeps you from getting to the strong coupling region near the fibranes. So as long as fibranes are separated on their Coulomb branch, the world sheet theory is perfectly fine, even though it looks like naively from the low energy supergravity point of view that there's a line singularity with a fibrane pole in the harmonic functions. So I think I've said everything here. So the next thing to do is to introduce the second charge, because we're interested in not just fibranes on their Coulomb branch, but NS5P supertubes, and then their NS5 F1 T-duals. So we build this up in a two-step process. The first is that we need to get the fibranes to be not entirely in the Y direction, but a little bit into the transverse directions. And this is accomplished by just generalizing the structure of the gauged Wessamino-Witten model from a gauge group that lives entirely in the transverse SL2 cross SU2, but also has a component partly in T and S1Y. So we're going to tilt the gauging. We're going to keep it null, but just tilt it from being partly in the transverse factor to be partly also in the longitudinal factor. So that'll accomplish this. It'll change the source from being parallel to the Y direction to being tilted into both the Y and transverse directions. And then we'll perform a T-duality, and that'll convert things into the geometry that we want, which has a linear dilaton throat, an ADS3 cap, and similar to the GMR geometries that Pierre was talking about in the last talk, has a ZK orbifold singularity at the bottom of the throat. And so this is very nice because it's quite rare to have a bulk description of states in string theory that are far from the vacuum and yet are exactly solvable in worldsheet string theory. The set of states that we're getting, k equals 1, is this state that lives at the edge of the BPS line. It's maximally spinning. If you try to go further, you exceed the unitarity bounds of the space-time CFT. And then as you increase k, you march inexorably towards the extremal BTZ black hole. As k gets larger and larger, basically you're getting the angular momentum of the source is N1, N5 over k. So as I say, we build this up in steps. We start with the NS fibranes on the Coulomb branch. Then we tilt the gauging. So we add a component which is a null vector in the TY directions with a very particular coefficient. And then subsequently, we do a T-duality, which changes Y to its T-dual and changes the sign of the left moving component. And so that takes us, after we eliminate the gauge field in the way I described for the Luna-Matur geometries, we get a Luna-Matur geometry back, but with a slightly different harmonic function. And instead of the SL2 coordinates, which we've removed, they got replaced by the TY coordinates. So instead of getting rid of the transverse bit like you do on the Coulomb branch, you get back a transverse bit now with a one-brane harmonic function that's related to the group theory that you started with. What happens to the dual Landau-Ginzburg description? Well, it's very simple to describe. You take the coordinates t plus y that you've added to the gauging. You now have a new superpotential, which is just a slight modification of the old one, where the momentum, if you like, in the NS5P picture gets tacked onto the Landau-Ginzburg field Z, and this does exactly what you want. So if you ask, where are the zeros of the superpotential? Well, they're still at the roots of unity, so they're still distributed around a circle. But now as I go up the V direction, they adiabatically rotate by some amount. And the K over N5 just says that by the time I get to 2 pi Ry, I pop back down to the periodic identification, but I've hopped over K5 branes. And if K and N5 are relatively prime, then this wraps my N5 5-branes into a single 5-brane supertube. And I'll continue to draw this picture, which is really from the NS5P frame, but you should think of that as being T-dual to the NS5F1 frame, but that the T-duality, the exact T-duality of the worldsheet theory keeps track of exactly where the 5-branes are and what they're doing. Now, it's not too much of a leap to say, what does a general supertube look like? Well, in the Landau-Ginzburg picture, it should just correspond to giving a more generic wiggly shape to the superpotential. So if we allow the zeros of the superpotential to now have some more generic oscillation as a function of V, subject to a twisted periodic boundary condition, that this will describe the near source structure on the worldsheet in the worldsheet theory corresponding to a generic supertube, which just has an NS background turned on. And indeed, that's the case. And so this is a demonstration that in fact, this worldsheet FZZ duality that relates the Luhmann-Motor geometries to a dual Landau-Ginzburg description is not special to the round supertube or the round array and the Coulomb branch. It's a generic feature of the half BPS configuration space. And so the thing that's doing the work here is the source profile F of V in the NS5P frame. It's on the one hand, it codes through the Luhmann-Motor Green's function integrals the harmonic forms and functions of the Luhmann-Motor geometry. At the same time, it codes the structure of the superpotential in a dual description that knows about the stringy structure near the source. Now, recall that supertubes are labeled by 5-brane excitation state. For the bosonic modes, we have these transverse scalar modes, and we have these internal modes, which are the NS5 tensor gauge field and an additional scalar. The supertube corresponds to a very particular state of those modes where we've taken a single mode, which, as I mentioned at the beginning, is basically a kth Fourier mode of x1 plus ix2, and we've excited it a macroscopic number of times. K, remember, was the orbifolding of the ADS3 cap. So, so that's the state we have to start with. But we have an exact worldsheet conformal field theory. So we have a complete list of the vertex operators that describe string states in this background. And among those vertex operators, you can identify those that implement the transitions between this starting state and perturbatively around this state, these more general supertubes. So they're vertex operators. They're basically the half BPS vertex operators of the half BPS background, preserve the half BPS property. And you can write them out explicitly in group theoretic terms. And so these perturbations take us towards arbitrary half BPS backgrounds starting from the round supertube. More explicitly, what these look like are, well, I have a bunch of solvable conformal field theories, and vertex operators in worldsheet string theory consist of some center of mass wave function. In this case, there'll be group harmonics on the group manifold times some plane wave exponentials in the longitudinal coordinates. And then if I'm going to specify, say, a supergraviton, I need a couple of oscillator excitations, which tell me, which are the, carry on the operator excitation, what is the polarization of the particular graviton mode that I'm exciting. And the BPS ones happen to be that keep my excitation of the supertube in the 1-2 plane, have either both oscillator polarizations in SL2 with this particular correlation between the center of mass and the polarization of the SL2 currents, or this particular combination of the SU2 polarizations. If I have one from each, then that describes excitations which start moving the supertube in the 3-4 direction. So anyways, there's a complete list. Among that list is the zero mode of the dilaton, which plays a role in the space-time CFT. It basically counts the number of strings in the background because that's a fixed scalar. So this, if you like, has some kind of expectation value, which is related to the space-time CFT's central charge. And for aficionados of superstrata, the anti-symmetric combination of the Ramon-Ramon scalar, Ramon-Ramon operators is the Ramon-Ramon scalar that creates what superstrata literature calls a 0-0 excitation. And so those are in this setup are particular Ramon-Ramon operators. And so we don't turn them on because while they're simple to deal with in supergravity, they're a nightmare from the point of view of the worldsheet. And then the triplet partner of these are the triplet of antisymmetric tensor modes on the 5 brane. While we're at it, all of these half BPS vertex operators have quarter BPS generalizations. So what do those correspond to? Those correspond to keeping the BPS structure, say, in the right moving part of the worldsheet, but allowing something more general in the left moving part, okay? So if I go away from states that are highest weight on the left in the SU2 and SL2 factors, then that breaks the BPS symmetry on the left while keeping the BPS symmetry on the right because we keep the highest weight structure in the zero mode factors. And then in order to do so generically, I need to turn on some momentum on the Y circle. And so, so this will be something that carries both winding and momentum. So the states I start getting have quantum numbers NS5, F1, and P. So perturbatively turning on the third charge. And now in general, I can have as much of this momentum as you want at possibly the cost of exciting more generic oscillator modes on the left. But that's okay. I'm doing worldsheet string theory and I have complete control over it, so why not? So among this list of vertex operators, there's a small subset which correspond to supergravity excitations, where the left moving oscillation is a single oscillator excitation in the first oscillator level that describes a supergraviton just of a more general polarization than the BPS ones. It's still BPS on the right, but not BPS on the left. And so among those are supergravity modes. And they have the quantum numbers, and among those supergravity modes are the ones that people turn on to describe superstrata. But there are more than those. And so that suggests that awaiting us are more and more general supergravity geometries, which are, morally speaking, the brothers and sisters of the superstrata that have been described to date. So on the worldsheet, these are deformations that preserve all the supersymmetry that you had to begin with, but break some of the supersymmetry on the left. And all of those modes still have FCZ duals. They're now described by a 0.4 or 0.2 Landau-Ginzburg theory. So all of this structure I'm describing is expected to carry over to describing more general superstrata and even stringy versions of superstrata. The number of these quarter BPS excitations is counted by the elliptic genus. And so that's something that we're exploring the possibility of working out. Since we have an exact worldsheet theory, it shouldn't be too hard. And I should just say, in general, there's a terminology which was arrived at by Benna and Warner, that there's sort of a hierarchy of things in terms of complexity of the microstate structure. The least complex and yet already pretty daunting are the microstate geometries, which we've been hearing about in various talks at this workshop. And then there's what you might call stringy microstate solutions, which I would argue the things I'm describing here are of that class, the things which I make, where I make perturbative stringy excitations around a geometric background. And if one could then solve for the space-time that's sourced by that, I argue that the Landau-Ginzburg picture tells me it would still be not singular. And so I would have some kind of a stringy background, which is not singular. And then there are things that are more generic, I would argue, than that, which have where I think the bulk of the entropy of quarter BPS states are. And I think you can see where they come from and where these particular simpler things fail to describe them. And it's to that issue that I'd like to turn now. But maybe before I do that, I should pause and ask if there are any questions so far.
I had a question about the expectation about the fact that things are going to be very stringy and hard to describe. Do you see this coming from the choppiness of the profile, or do you see? I mean, I'm just wondering where is that coming from. In the two-charge system, for example, we know that the reason why I don't trust typical two-charge geometries is because the supertube profile is very choppy. Essentially, it has Fourier frequencies higher than higher than some number which makes Planck size wiggles. I'm just wondering if you can see from this approach, any sign of that.
So I would say there's sort of a continuum. So when the angular momentum is large, so when K is so if we go back to this picture, so the states we're getting when K equals 1, we're here. The supertube is enormous. It's some big circle. And as you increase K, it's basically what's happening is that you're jumping over, as you go up here, you jump over K5 branes before you periodically identify. Mm-hmm. So as you make K bigger and bigger, the supertube spiral is getting more and more flat and more windy as you pile in here. And so the stringiness of the structure is that the that fact that the supertube is running over the same profile more and more times as you make K bigger and bigger means this orbifold singularity is getting more and more conically steep. Mm-hmm. Okay. And so all of the stringy structure is happening in the cap, but the worldsheet theory doesn't care. I have this exact Wessamino-Witten model. So there's some very stringy orbifold structure here, and then some smoother geometry further out. Now, granted, this is a very special round supertube. If I start going to these more generic profiles, then basically if I just using it, if I'm just making it with sort of the low kx, the low frequency excitations of the supertube, then it's going to be big and fat and carry lots of angular momentum, and it's going to be describable by supergravity even near the source. But as I start using momentum modes on the profile that are bigger and bigger, the source gets more and more compact, and the near source region gets more and more stringy. Okay.
But the momentum usually back reacts and, usually makes gives a throat and, keeps the solution from becoming too stringy, because, the momentum also back reacts and, puffs up the configuration.
Yeah, so there's a question of, okay, how far can I go with these quarter BPS excitations without, having to worry seriously about the back reaction and what that does. So for me, there's the quarter BPS generalization of the Lunen-Motor solution, which is the GMR solution that has been the subject of the previous talks. And my claim is that that is dual to some Landau-Ginzburg theory. And it's just a 0-4 Landau-Ginzburg theory. And so I think that if I find singularities of the half BPS geometries, which we're about to discuss, I think there will also be singularities of the quarter BPS geometries that are well beyond supergravity. But they'll still be describable in the worldsheet theory because I have a Landau-Ginzburg picture, and the singularities were going to be coming from the generation of the Landau-Ginzburg superpotential. So, I think the worldsheet formalism, what we may lose track of is precisely what Landau-Ginzburg theory corresponds to what particular geometry. But I think even when situation becomes stringy, I think there will be situations where there are Superstrata or Microstate solutions that are stringy that just adding the third charge always going to help you. And in fact, I think there are even worse issues than that. That there are places where just even perturbative string theory breaks down, and that's where the bulk of the states are hiding.
Okay.
So let me turn to a discussion then of potential singularities in this picture. Okay. So we have two pictures, and they're dual to one another in a quantum equivalence of worldsheet theories. One is this Landau-Ginzburg description, and one is the geometric description of Lunen-Motor. And so let me describe from both points of view where a singularity comes from. So in the geometric picture, the T-duality of this NS5P picture took us to some situation where the explicit fibrane source, which is staring you in the face with this profile f of v, gets turned into some kind of Kaluza-Klein monopole, which is a codimension, which has a coordinate singularity in codimension 4. Okay, and f of v is basically describing the one extra dimension, which is among the 5 directions we're talking about, namely v, x1 through x4, that KKM core is sort of, wiggling around in the geometry, okay? And what can happen is that when the profile f of v self-intersects, then 2 of these KK monopole cores start coming close to one another. So here locally are the KK monopole core extending along a stretch of its contour, and it runs around and then maybe loops back and hits itself again, or comes near to hitting itself again. And so a pair of KK monopole cores, what is the KK monopole geometry? It's basically something that's completely smooth, but it's smooth in an interesting way. It's a circle fibered over R3. And as in all of these BPS geometries, the metric coefficients are given by harmonic functions. In this case, it's a harmonic function in R3. And where its pole is a place where the circle fibered over R3 degenerates. But it degenerates in a completely smooth way in this sort of capped geometry. And if I have a pair of KK monopole cores, then basically there's a homological S2 in the geometry, which is that this fibered circle shrinks away in the KK monopole core here, and it also shrinks away in a second KK monopole core here. And so just following that circle fibered over the interval stretching between the two KK monopole cores makes an S2. And as the KK monopole contour comes close to a self-intersection, that circle shrinks and shrinks and shrinks. And if there is an exact intersection of the profile, then that circle shrinks to 0 size. When that happens, then worldsheet strength theory breaks down because in the NS5F1 frame in type 2b, there are D3 branes. D3 branes can wrap that vanishing S2 and make what are sometimes called tensionless strings. And so in that process, worldsheet string theory breaks down. What are these tensionless strings? Well, what we have in the dual picture is two 5 branes coming together, and the D3 branes in the T-dual NS5P picture are D2 branes that are stretching between the 5 branes. And again, once the profile self-intersects, that D2 brane stretch between the 5 branes becomes once again a picture of the tensionless string, which is just what you might call the W string of the underlying little string theory. And so what we meet here is what's been sort of hiding from this microstate geometry picture, which is the bulk of the entropy of all the microstates. And the place where it's hiding is in the Hagedorn entropy of little strings. If you ask what are black 5 branes, Juan Maldacena showed quite a while ago that you could account for the entropy of black 5 branes by thinking about a Hagedorn gas of little strings. And these are those little strings. They're popping up in the cap as an object in the ADS3 limit, but they're governing the non-perturbative physics in regimes where the underlying 5 branes get too close to one another. So that's the picture from the Lunenburg geometric side. On the Landau-Ginzburg side, what's happening is that where the 5 branes are is coded in the zeros of the superpotential. So we can just expand the superpotential when 2 zeros of the superpotential come nearby, say 2 of the zeros at mu naught plus epsilon and mu naught minus epsilon at some particular value of the profile V coordinate, then along the direction of the common 0, the Liouville wall goes away. If I construct the bosonic potential from this superpotential by taking its absolute square of its gradient, then what you find is indeed a Liouville wall, but its coefficient goes like epsilon to the 4th. So remember, it was the Liouville wall that was keeping you from exploring the strong coupling region of the linear dilaton in Liouville theory. As the 2 zeros come closer together, as the 5 branes come together, that Liouville wall gets weaker and weaker. You have to go further and further into it before you, if you have some energy, you go further and further into it and further into the strong coupling region before you bounce back out to weak coupling. And so once again, you see that worldsheet perturbation theory is breaking down because 5 branes are coming close together. And so the lesson here is that to get sort of little subthroats that perturbative strings can get into needs at least 2 5 branes. there's no world sheet theory of a single fibrane. And so what's happened is when you separated the fibranes apart onto their Coulomb branch, you created an effective wall that keeps strings from probing the region near the fibranes where they become strongly coupled. And once you let the fibranes start to coalesce, then you create a little throat, which is just big enough for a string to get into, and it can go down that throat and reach a strong coupling region where perturbation theory breaks down. And in this dual Landau-Ginzburg picture, this little throat has FZZ duals of these wrapped D branes in the geometric picture. What they are what are called the ZZ branes of Liouville theory. They're branes that are sort of pinned to the strong coupling region. And they're fine as long as you have the Liouville wall, but if you take away the Liouville wall, they become singular. And all of this is very reminiscent of a structure that one sees in the what's called the C=1 matrix model of non-critical string theory. There too, one had a Liouville wall. There, the matrix model was exactly solvable, and you had a picture of collective excitations of the eigenvalues of the matrix describing closed strings in the bulk of space-time. And then as you got to the Liouville wall, there could be non-perturbative processes. The non-perturbative process, you start to see the individual eigenvalues of the matrix, which are the D branes of the underlying gauge gravity duality. And the interesting non-perturbative structure has to do with those D branes. You have something very similar going on here, where the interesting non-perturbative physics of fibranes is governed by D branes that live in the strong coupling region. Now, another piece of our project was to put some flesh on this. I've sort of hand waved a bit, saying, well, there's this Landau-Ginzburg picture, and we should understand that it's dual to some geometrical picture. All of that can be made very explicit for one particular deformation where we were still sufficiently grounded in symmetry to be able to solve things exactly. And that's the deformation where you take the round array of fibranes and you squash it into an ellipse. And so the profile deforms to something elliptical. And we were able to determine exact expressions for all the harmonic functions in the Lunin-Latour solution. And we were able to identify the S2 that vanishes when you take the extreme limit of the eccentricity of the ellipse going to 0. The state in the space-time CFT that this is related to is a deformation of the round supertube where you start incorporating other modes of excitation. And the A1 and A2 parameters of the profile and the geometry are just coherent state parameters related to the number of the different kinds of modes. When the ellipse degenerates, then the D brane that stretches between the fibrane becomes massless. We're able to verify this explicitly through a dBi calculation in the corresponding Lunin-Latour geometry. And you can do the same thing on the Landau-Ginzburg side by constructing the Landau-Ginzburg superpotential that corresponds to this elliptical array of sources and watching it degenerate. So everything's very, very sort of pleasingly consistent. I should say in this Gage-Wessamino-Witten model picture, there's kind of a funky presentation of the D branes. D branes in the Wessamino-Witten model are, again, because it's exactly solvable, not surprisingly, there are certain D brane states which can be exactly solved. The D branes live on conjugacy classes of the group, which are just particular nice symmetric spaces. So for instance, two spheres living inside S3 or hyperboloids living inside ADS3. And so this gives kind of an interesting geometrical picture to what in the projected theory are D branes stretching between fibranes. in the gauge invariant picture upstairs, well, the D branes have to be gauge invariant. So you have to extend them along the gauge orbit so that they have an isometry that can be projected down to the effective geometry downstairs. So what's happening is this geometric, as the phi get squashed and the ellipse gets squashed, this two-sphere in the underlying sigma model on the world sheet, that two-sphere just gets shrunk to 0 size as the ellipse degenerates. Okay, so the ellipse degeneration is still not very generic, but as soon as you start turning on more and more modes, the degeneration starts looking more and more generic, and it happens whenever, as I was saying, the 5-brane supertube loop starts to self-intersect.
Emil, we're coming up on a bit past the hour at this point, so.
Okay, well, so I just have, can I have about 5 more minutes?
Oh, 10 minutes is fine, don't worry. But
yeah, we're just about there. But one thing I wanted to point out is that one process that can happen is that basically you have a stack of 5-branes now that's intersecting itself locally in the geometry. And at that point, the branes that stretch between the 5-branes become light, they can condense. And this is just the S-dual of a process we know very well in D-brane physics, where if I have 2 D-branes that self-intersect, the open strings that stretch between them become light and can condense. And what does that do? That does something where 2 D-branes you have a process where as the D-brane starts to self-intersect, the open strings that live at the intersection condense, and that describes a process where the D-brane can split into 2 D-branes, okay? And so among the non-perturbative processes that can happen here is the S-dual of that joining splitting process, where a single stack of 5-branes can turn into 2 stacks of 5-branes. So let me just conclude then with where I think all of this is headed and how it connects to fuzzballs. So in its most broad incarnation, the fuzzball proposal is just some assertion that string theory naturally generates objects whose quantum wave function is delocalized on the black hole horizon scale, and that so there are structures in string theory which persist at the horizon in a way that can't happen in ordinary gravity. In ordinary gravity, everything is forced to collapse into the singularity. But in string theory, you have objects which are potentially non-local on the horizon scale and therefore could radiate coherently from that scale and explain the unitarity of Hawking radiation. Now, most of the explorations that have been made to date have focused on the geometrical side of things. Supergravity has a lot of power to describe more general configurations than one can solve for in world sheet string theory. And the large class that's been explored to date has been discussed in detail by, for instance, Pierre Heidmann in the previous talk and Daniel Meyerson yesterday. And they basically have the structure that you take a supertube and then you decorate it with a momentum wave that's running around the cap of the geometry. But as I've tried to argue here, these topological solitons with flux are only part of the story. They're very coherent states. They're things where you have, just a few modes of the supertube excited, and then you decorate it with some momentum waves. And what the Superstrata people are embarked on doing is a program of making the wave quanta more and more generic, but not making the underlying supertube more generic. And so I claim that there are BPS deformations which will take the underlying supertube of the superstratum and start wiggling its shape. Those excitations haven't been studied to date. To date, people have been mostly focused on supergravity modes. Well, for instance, Pierre's talk. He was looking at supergravity modes where he took the polarization of the graviton on the T4 so he could dimensionally reduce to get a scalar wave equation. And his evanescent ergo surface modes were just the lowest modes sitting in the cap near this, and they were basically the evanescent ergo surface is the supertube. And what I'm claiming and what we've shown in the paper is that if we instead focus on gravitons whose polarizations are in the ambient transverse space, that the BPS versions of those modes are things that deform the shape of the supertube. They live at, again, at the evanescent ergo surface. That's not surprised, that's where the supertube is. And so if you're gonna be deforming the supertube, the modes that do that are exponentially concentrated around the supertube itself. And so these are sort of the tensor cousins of the modes that Pierre was talking about. So the claim is then that among the half BPS deformations, or even quarter BPS deformations, are those that evolve the supertube along its moduli space. And I suspect also evolve the fuzzball in its shape space. And it'll start diffusing around the available phase space. It'll keep doing that, it'll keep wiggling around, oscillating in the transverse space until it comes close to a self-intersection that you have non-perturbative D-brane creation processes going on. And then one needs to understand the D-brane excitations. And I think what this is indicative of is something that's been encountered in ADS2 situations where there are relations to D-brane physics and quiver quantum mechanics. This is just sort of a much fancier version involving effective strings rather than in effective D particles. But it's very much the same thing. The geometry is capped off because you've pushed the system onto its Coulomb branch. And as we've seen from the Landau-Ginzburg picture, the effect of putting the fibranes on their Coulomb branch is to cap off the geometry with some kind of a wall. And what happens when the fibrane profile self-intersects is that the wall goes away. Strong coupling is available. There are new degrees of freedom. They're stringy. They're in fact precisely the degrees of freedom that you expect to be the ones that are the dominant actors in the entropy of black holes. And they're to use the same terminology that people used in quiver quantum mechanics. The quiver quantum mechanics had a Coulomb branch and a Higgs branch. The Coulomb branch had some small number of microstates. The Higgs branch had exponentially more. And where they intersect is where the Coulomb branch configurations have the D-brane source, the brane sources come together where the Higgs branch excitations become light and condense. And so we're seeing very much the same picture here. Everything I said for half BPS, we're expecting to carry over to quarter BPS. And the question is whether we have enough power to start identifying particular geometrical profiles of superstrata with specific Landau-Ginzburg models. So in particular, one process that can happen, as I was saying, is that if we have a big supertube that's carrying lots of angular momentum, it wanders around its configuration space until it splits into two pieces by a fibrane joining splitting process. Then one end state which is available to you is that there are, say, some red 5 parts of the fibrane world volume that carry away all of the angular momentum into a half BPS supertube. And the remaining bits of fibrane form something which has very low angular momentum. And then you start getting into the BTZ regime where there's lots of entropy available, but simultaneously, because you've carried away most of the angular momentum, the fibranes are on top of each other, and you have to deal with the little strings that are getting excited in the core. So to summarize, there's a geometrical regime of smooth geometries with a capped throat. It's separated from the black hole regime by something of a phase transition, which is familiar from all our other examples of gauge gravity duality. If there's a weak coupling version of the brane dynamics, this looks like deconfinement of the non-abelian brane degrees of freedom. The degrees of freedom arise where the supergravity, so in things that are smooth geometries, those degrees of freedom are in some sense confined. And there's a perfectly good effective theory in terms of the collective coordinates, which are the supergravity modes. And then the place where black holes want to form, those degrees of freedom reemerge. And they reemerge because they're the entropic degrees of freedom of the black hole. And what we're starting to see is in a controlled string theory analysis, we're starting to see those degrees of freedom emerging on the gravity side of the duality. And so one question I have is the horizon the boundary of such a deconfined phase? And if so, by analyzing the low energy supergravity and trying to analytically continue it to the interior of the black hole, are we in some sense analytically continuing the wrong phase across a phase boundary? Time will tell, but the fuzzball paradigm asserts that the scale of the branes that are getting excited has is some quantum object whose wave function is the horizon scale. And our hope is that if we can learn enough about D-branes in these particular stringy backgrounds, that we'll be able to provide some evidence for that assertion. But that lies in the future, and I thank you for your attention.
Thank you, Emil. That was very good. Questions?
Yeah, so I have a question about the beginning of the talk. So you started by constructing Weismann-Witten models where both U and V are like killing vectors.
Yes.
What is the hope, or like, is there any constructions where you only take one of them, like in the more general superstratum, and like, can you construct Weismann-Witten models in that case and follow your logic to the rest of the talk?
So far, the things that have exact solutions related to Weismann-Witten models include the ones that I've described, but also there's one more generalization you can do that describes the Justum-Sur-Saxena geometries that Pierre talked about in his talk. So there are three charge geometries that you get from what's called spectral flow in the ADS3. And those are also described in this formalism. That basically correspond to, so the class I described are where you have a null vector in the target space that you're gauging, but it's null in ADS3 cross S3, and it's also null in RTY. If you generalize the null vector further to one that's not null separately in ADS3 cross S3 and in RTY, but just null overall. So it's say time like here and space like here, or vice versa, but null overall. That generalization describes the GMS geometries. And we worked that out in the papers that I referred to on the first slide. So there are three charged things. They don't have this long ADS2 throat. So the ADS2 throat is specific to superstrata, which, because they require these so-called 0-0 strands, they involve Ramon excitations, and they're difficult to deal with from the world sheet point of view.
Mm-hmm. So basically, whenever you don't have Ramon charges, you can always cook up a Weismann-Witten model that will describe the physics. That you can solve also.
So there are particular examples. So basically, in this phase diagram, the ones I described today are living here on this half BPS line. the spectral flow geometries, the GMS geometries, live along a parabola which takes you parallel to but slightly below the BTZ threshold.
Mm-hmm.
Any more questions or comments?
Can I ask?
Go ahead.
I personally have a question.
Hang on a second. Masaki was, I think, asking a question. So hold a sec.
Yeah.
Masaki.
Can I? Yeah. Toward the end of the talk, it sounded like you're headed to multi-center solutions because you talked about splitting and joining of NS5, right? And I even saw you wrote multi-bubbles on the slide. But on the other hand, there's this Guillaume-Bossard's result that multi-center solutions don't correspond to indexed states. So they don't exist everywhere in the moduli space. So that sounds like these multi-center solutions are not exactly what we want. So then what do you think are the states that we have to really look for? So it should certainly be something that is happening when some strands of NS5 branes are close to each other. And do you think that we have to really consider not just joining and splitting, but we have to consider some more stringy thing happening when two strands are close to each other? That's not visible in supergravity. What do you have in mind?
So yeah, so this sort of dynamics where the fibranes are moving around on the moduli space is inherently not BPS. Right? I have this enormous phase space of half BPS solutions, right? I have exponentially many half BPS states. And so there's an enormous phase space, and I can start exploring that phase space if I kick the solution a little bit. So this, stable trapping phenomenon that Pierre was discussing, to my mind, is just code for you kick the geometry a little bit. It now has a little bit of energy. And what do you do, in collective coordinate dynamics? It's you say, okay, I take make a moduli space approximation, and I let the system be described by the half BPS configurations. But now I introduce some slight non-BPSness by letting the collective coordinates have some velocity on the moduli space. And so, something can last for a very long time just exploring the half BPS configuration space, diffusing around amongst the exponentially many states available. And that's some kind of near extremal scrambling process.
Yeah, but do we have to consider such a process? We can just consider some BPS configuration, which is really close to, we can really consider a BPS configuration that is near this configuration where two strands intersect. We are free to consider any point in the moduli space. So
yes. And so what I'm saying is that if you're sufficiently away from BPS that you can push two fibrane strands. So it might be that configurations where the fibranes are on top of each other aren't BPS. Maybe that the way things work out is that they're a Planck distance away from each other. Okay. Well, first of all, you probably don't trust supergravity or maybe even string theory in that situation. Well, perturbative string theory. But as soon as you give the system a little, kick, you can give it enough energy that you push the strands onto one another, and then this joining splitting process is one of the possible outcomes. Now, whether it stays in that configuration or wants to relax back into something single-centered is, something well beyond our techniques at the moment to resolve. But I'm giving you a picture of what the configuration space looks like and what its approximate energetics is from this Landau-Ginzburg picture.
So you're not really talking about what is going to happen when we consider a BPS configuration where two strands really intersect exactly.
As I say, there may be BPS configurations that require you to consider such configurations. They're well beyond supergravity.
Sure, sure.
Well beyond perturbative string theory.
Yeah. Okay.
I should say that none of the structure I described here is apparent by thinking about the symmetric orbifold conformal field theory. That's way off in some other cusp of the moduli space of the space-time CFT, where the effective description is in terms of a single 5-brane and n strings. And a single 5-brane can't intersect itself. It's executing this wiggly profile, but there's only one 5-brane. So it can't intersect itself in a BPS way. You have to go off BPS in order to do that. So I think maybe part of the answer to your question is if your intuition is coming from the symmetric orbifold, that intuition doesn't apply here because we're very far away in the moduli space of the space-time CFT, where there's more than one 5-brane in the background in the effective description. And now there are these processes where things can self-intersect in a very close to BPS way that's not available in the symmetric orbifold.
Okay, I will think about that. Thanks.
So any further comments?
If I can just maybe it's extremely related to the previous one, but so as long as I understand, the Wachi description, the perturbative Wachi description works in as long as the 5-branes are on the Coulomb branch, and as long as a couple of sparse 5-branes merge, this description breaks down because the Liouville potential is not zero vanishes, and there's no wall that prevents the strings to enter the strong coupling region. So my question is, do you think is any way to explore in this formalism the strong coupling region of merging of five, or extreme? I mean, even when they are extremely small, because this is if I understood correctly, this is the region where we have the most entropic contribution to the black hole, which is in the Higgs space, essentially.
Yeah, it's sort of a question of whether can we learn something about little string theory in this regime. I think there's always going to be some kind of strong coupling physics, and it's going to be related to 5+1 gauge theory, right? These are particular BPS and near BPS states of a 5+1 gauge theory wrapped on some skewed T5 where you've got a T4 and then some other circle which is much bigger than the T4. That's sort of the regime we're working in, okay? And so you're looking at 5-branes that are wrapped on that asymmetric T5, and you're looking at the light excitations. And the light excitations are going to be things where you have to deal with the non-abelian structure in this regime. When the 5-branes start coming together, all the non-abelian structure of the 5-branes starts coming. You were able to avoid thinking about it by being on the Coulomb branch. And I claim that all of these cap geometries are in some sense Coulomb branch configurations in disguise. And so for me, their interest lies in that there are things which are very coherent states. You can even make them having the quantum numbers of black holes. You can push yourself into the BTZ region on the phase plot that I drew. And so there's like very particular BPS coherent starting points for asking questions about how does the system become a black hole? And so, there are these trapped modes that are stably trapped for long times, start scrambling around in the bottom of the geometry. But you don't have the full entropy of the black hole configurations. And so certain things that have to do with, having the full phase space of black holes available are not going to be available, I suspect, in thinking about superstrata or even these stringy extensions of them, but involves some strong coupling physics for which we need a good idea how to solve for 5+1 gauge theory, on the and somebody has a good idea how to solve the 2-0 theory, I'm all ears.
I have a problem with this Coulomb branch interpretation, because the point is, if you look at superstrata which have a long throat, the mass gap they have is 1/n1 and 5. There is no way anywhere in string theory out of branes on a Coulomb branch you can get the mass gap which is 1/n1 times n5. Coulomb branch branes have a mass gap of order 1. So I don't think this Coulomb branch argument, it may look Coulomb branchy, but clearly when you have something which has a mass gap 1/n1 and 5, that thing cannot be Coulomb branch. Maybe it was Coulomb branch at the orbifold point and it migrated into the Higgs branch in the supergravity point. Maybe there's a movement between the branches, but something which has mass gap 1/n1 and 5, there's no way to realize that on a Coulomb branch.
You are forcing the system into the straitjacket of round supertube bases. And I think as soon as you allow the system to start deforming along its moduli space away from the round supertube, you will find that the phenomenon that I was describing will take place. And it's probably not the place to do it here, but I'd be happy to describe the route by which I think the superstrata that you and Nick and others have been exploring can decay and find this sort of self-intersection and the corresponding strong coupling physics.
By this decay, you mean that the supertube starts self-intersecting and maybe generates these
yeah,
extra bubbles.
Okay, so
extra bubbles, they don't need to be Gibbon-sucking bubbles,
But okay, hold on a sec. There was this, so there seem to be two separate statements I just want to get clarity on. There are multi-centered, multi-bubble solutions, which we know lift very slightly if you go to generic points in the moduli space.
Yeah.
What do they represent in the scheme of things that you're talking about?
So my guess is that they correspond to these situations where the underlying 5-brane source has multiple distinct 5 branes, okay? And that the question is whether these multi-bubble things will have soft shape modes that will provide you a route through a near BPS configurations space where they can self-intersect, either self-intersect or intersect with each other. So that's something that I'd like to explore further and see if there's, and I'd like to understand just in general, what is, the multi-bubble solutions that you guys first started exploring, in the mid 2000s. I'd like to understand in a, much better how they fit into the picture I've been presenting. At the moment, I don't have a clear picture, just a suspicion that because they have 5 branes underneath, that the 5 branes can do this sort of thing, and that there will be paths by which you can get some bubbles in the geometry to shrink down and get some massless brane excitations. If that's not true, if there's some kind of stable islands where these bubbles are sort of rigid, that too would be very interesting. That would mean that sort of within the microstate phase space, there are stable geometries that have bubbles that you can excite at least a little bit, and they don't fall apart into more generic black holes. So if there were sort of islands of KAM stability within a larger sea of chaos, I think that would be interesting as well. My suspicion is that they can all decay.
So how does that address Joseph's comment about the fact that the mass gap in these deep superstrata is 1/n1/5? Do you suddenly lift this mass gap up to something of order 1 in the decay process?
No. It's quite the opposite. So I'm saying that when two 5-brain strands get close together, there's a way for a string to get closer and closer to the 5 brains. So the gap goes down in that process.
Surely it better not go down below 1 over M1N5. It better not go less than 1 over the central charge of the theory.
Well, you get to a regime where you start exciting D brains and you lose control over the perturbative calculation. So the physics is D brain condensates from this in this duality frame.
Got it. Any more questions from not the usual suspect? Any comments? Well, we have a panel in 10 minutes, so let's all take a 10-minute break and reconvene at 5:45, and I'll see you then.
I think we can leave the we can leave the YouTube going since it's only 10 minutes. No, actually, no. It's half an hour the panel, right? Oh,
no, it's 10 minutes. 10 minutes.
Okay. We'll leave the YouTube going then. So I'll just mute everybody and we'll leave the YouTube going.
Heineck, you tell me when we should start.
I will in a few minutes.
I guess the round table started already after Emil's talk.
And began a bit. I think it's going to be, we might be a minute or two late. I think people just need a little bit longer break, but we'll start in a couple of minutes. And,
how are you?
Oh, I'm doing very well, actually. It's a beautiful day, you know.
Yeah, it's a very nice meeting too. You know,
oh, good.
Some nice stuff, yeah.
I'm enjoying it a lot, so it's great.
Yeah.
But I must admit, you know, when we set this up, I thought, well, I don't want more than about 3 talks a day in a panel, because I was I'd read about Zoom fatigue, and yeah, it's noticeable. It's harder to keep focus on Zoom than for long periods of time.
It is actually, yeah. I think 3 talks per day is probably the upper bound. You know?
Yeah, I really think so. Normally, you know, I can go for a whole day of the conference, and maybe I'll need to duck a talk the next day. But this is intense. But you know, it's great.
Very nice.
So, Joseph, are you around?
Yes, I'm here. I just made Douglas and Ben. I made them co-hosts.
Do we have everybody? There's Ben. I can see Douglas. I just want to say thank you to Douglas. It's early morning, and he has to be functional. So thank you for being part of this, Douglas. So I just want to remind you, before we start, just want to remind you, tomorrow we have a slightly altered schedule. And that's we only start at 2:30 or 14:30 in the afternoon. So with that, I've just again, the basic idea of the panel is to have 4 or 5 people start a discussion along a particular topic. So we let the 4 or 5 panelists speak for 5 minutes or so each, and then we just start kicking around ideas. So basically, unless it's a really important question, hold your questions till the end and let the panelists discuss, start the discussion, and then we'll go from there after they're done. Okay, so I'll hand over to Kostas, who's moderating.
Okay, so I guess I will follow the alphabetic order, which is an order by first name, not last name, I realized. So Ben is supposed to start. And as Nick said, each of the speakers can give a short presentation of his view, and then we can open the floor to the discussion. So Ben, are you around?
Can you hear me, Kostas?
Yes, I can. Please.
Okay.
Nice background.
We're all good. Go for it.
Are my slides visible?
Yes.
Yes. Yes.
All right. So first of all, thanks Nick and Yossi for the invitation to this stimulating conference. In the first talk today, we saw Lyapunov exponents that quantifies the instability of the photon sphere. And for black holes in asymptotically flat space, this instability has been related to quasi-normal mode decay. Now, these are very interesting results, but to me, this manifestation of chaos via quasi-normal modes appears conceptually a bit different from the Lyapunov growth of commutator squared. So to argue for this, I will borrow a picture from Polchinski. So the commutator squared of operators V and W separated by a time t in a non-extremal black hole background displays 2 exponential behaviors. So one is the quasi-normal mode decay, which describes the late time relaxation that is also present in, for instance, retarded 2-point functions. The second is transient Lyapunov growth, for which one needs 4-point functions with non-standard time ordering. Now, while quasi-normal modes decay constants tend to be of order the temperature, up to numerical factors of order 1, the Lyapunov exponent is determined exactly by the temperature. And this reflects the fact that quasi-normal modes depend on what happens in some region outside the horizon, whereas the transient Lyapunov growth arises from the geometry at the location of the horizon. Now, because Lyapunov growth of the commutator squared captures what happens at black hole horizons, it would be very interesting to see how it differs between black holes and microstate geometries. So let me just make a few preliminary observations on that. First, let me remind you that for times large compared to the inverse temperature, the normalized commutator squared is simply given by 1 minus the real part of the out of time order correlator. And this is because contributions like VWWV can be interpreted as a 2-point function of W of t in a state created by acting with the V of 0 on the thermal state. And this state behaves thermally after one waits a few thermal times, so this contribution factorizes. Now, next, let me point out that the commutator squared contains more structure than shown in the previous picture. In a 2D holographic CFT, if the conformal dimensions satisfy that HW is large compared to HV, which is large compared to 1, and the time is large compared to both the spatial separation and the inverse temperature, the OTOC was computed in a paper by Roberts and Stanford. And in this formula, C is the central charge, which is large. So at sufficiently early times, one gets Lyapunov behavior from 1/c expansion, and sufficiently late times, one clearly sees exponential quasi-normal mode decay. Now notice that for small enough times, and the condition is written here, the OTOC is well approximated by the exponential of I times a phase, which can be arranged to be arbitrarily large by choosing HV to be large enough. So for times large compared to the inverse temperature, the commutator squared is simply given by the sine squared of an exponential. So here I used the relation between OTOC and commutator squared that I told you before about. So this oscillates with exponentially increasing frequency until the approximation stops being valid and quasi-normal mode decay sets in.
There should be a 1/c inside the argument of the sign.
Yes, that I forgot. Right, thanks. So this increasing frequency followed by quasi-normal mode decay is somewhat reminiscent of the gravitational wave signal of black hole mergers, but of course, many details are very different. Now, it would be nice to see in which way this behavior of oscillations, well, Lyapunov growth followed by oscillations followed by quasi-normal mode decay is modified in microstates with a long throat. So this brings me to a complication, which is, of course, that the microstate geometries that are under the best control correspond to extremal black holes, for instance, the extremal BTZ. And those have 0 temperature, which make the Lyapunov and the quasi-normal mode decay of the OTOC power law rather than exponential. That's a behavior that Roberts and Stanford referred to as slow scrambling. I think it's still interesting to ask how the power law decay of the OTOC and the subsequent oscillations are modified in microstate geometries. However, the relation with the commutator squared is now less straightforward because contributions like VWWV no longer factorize because at strictly 0 temperature, time intervals are always shorter than the inverse temperature, so one doesn't see dissipation. Since exponential growth of the commutator squared is what has led to the link with chaos, it would be nice to have explicit microstate geometries of non-extremal black holes, even if they are near extremal. As long as the temperature is not strictly 0, one just has to wait long enough to see proper exponential Lyapunov growth. So one question for the experts is whether it's feasible at all to get near extremal microstate geometries under sufficient control to do this kind of computations. Now, when Josif and I exchanged some brief emails about this over the last few days, Josif suggested trying to get around this by asking a question we had actually also been asking ourselves, namely for extremal BTZ, one can associate a finite temperature to the right movers. So can't one translate this into some proper Lyapunov growth? And there's actually a number of papers that discuss this. And my tentative understanding, mostly from a paper by Mezei and Sharoshi, is that for sufficiently high right moving temperature, one should find a small sawtooth-like modulation on top of the power law growth, where the steep parts of the sawtooth correspond to brief periods of Lyapunov growth. But on average, the scrambling would be slow. So I think my 5 minutes are up, so I will end here.
Okay, thank you very much. Maybe we move on to Douglas and then we take questions in the end, if you agree. Ben.
Just 1 second, I want to allow people to unmute themselves. I'll just mute everybody and then people can just unmute themselves, the speakers. Yep, it's all fine.
Okay, I have the following kind of very tentative comments to make. So the question I'd like to discuss briefly is about the role of fuzzball or microstate geometries, in particular in their role in the description of chaos from a bulk perspective, quantum chaos. So one possible answer is that these microstate geometries or fuzzballs directly describe microstates, for example, energy eigenstates of the boundary theory. But I'd like to mention a sort of a different and vaguer possibility, which I first heard about from Steve Schenker. And this idea isn't really very well developed, but I just wanted to mention it in case it, anybody can take it further. So let's see. Okay, so let's forget about black holes for a second and think about a different system. So let's take some classical chaotic single particle billiard system. This is a system that's been studied for decades in the context of quantum chaos. So it's a nice thing to think about. And what it means is a particle bouncing around in some kind of weirdly shaped region so that the motion of the particle is chaotic because of the collisions with the walls. So this is a system that's been studied for a very long time. And one of the questions that people asked in the context of quantum chaos is, what is the role of the classical periodic orbits in the quantum theory? And a plausible but incorrect guess for this would have been that these classical solutions correspond directly to energy eigenstates of the quantum theory. They're sort of stationary configurations, they're periodic. So you might have thought that they were analogous to energy eigenstates in the quantum theory. But that's not true. The right answer is that they're sort of a complementary or dual set of variables to the energy eigenstates or the energy eigenvalues. They're a perfectly valid description of the system, but they do not correspond directly to energy eigenvalues or energy eigenstates. So the relation between them goes through the Gutzwiller trace formula, the Selberg trace formula for the special case of hyperbolic space. And it looks something like this. Let's imagine we're computing the partition function, z of beta, thermal partition function of this single particle billiard system. Then one way we can compute the partition function, if we know all the energy eigenvalues, is we can do the sum over all the energy eigenvalues, e to the minus beta e. Okay. But another way we can compute it using basically the path integral is the expression on the right here. There's some smooth piece that's determined by the area of the billiard stadium. And then there's a sum over periodic orbits of something like e to the minus the length squared of the orbit divided by beta. This expression here is extremely schematic, and we can discuss the right formula if you like. But it's a sum over orbits plus this smooth piece. And the expression on the right is a perfectly good description for the thermal partition function. It's in particular determined by the data of these periodic orbits. But the sum here, the sum over orbits, is not the same thing as the sum over energies. The orbits do not correspond to individual energies. Okay, so the reason I'm bringing this up here is that one could maybe consider a kind of wild extrapolation of this idea that for the case of black holes, maybe Z smooth of beta could be analogous to the standard black hole solution, and the sum over orbits in this term could be analogous to the contributions of fuzzball microstate geometries. So they wouldn't be directly computing the microstates or describing the microstates, but they would be another type of description. Okay. I want to mention also, because it's been useful in the history of quantum chaos, another type of example along these lines, which is even farther from black holes, but it's even more concrete. And the thing I like about it is that it highlights these two different sets of data. Like here we have the energy eigenvalues and the orbits. And those two different sets of data is very clear in this next example, which I'll end with. So this example is goes back to work of Berry and Keating, or the interpretation goes back to work of Berry and Keating. So let's take, this is about the Riemann zeta function. Let's take these values Sn to be the non-trivial zeros of the zeta function, and consider a partition function where we take the energies of the system to be the squares of those zeros, a bunch of these zeros, and we take the squares of them to be the energies. Then I'm not going to show you how exactly, but if you start with the formula for the Riemann zeta function as a product over primes, then you can write the following formula for this partition function here. There's some e to the beta over 4 piece. There's this piece I'm calling Z smooth. And then there's a sum similar to the sum over periodic orbits. The data that replaces the length of the orbit is the value of prime P. So in this example, the two sort of complementary sets of data are the zeros of the zeta function and the primes. Okay, so let me just end with a summary of this vague idea. So we sort of briefly discussed these three different types of systems. And in the case of billiards, and in the case of the zeta function, there are these two different types of sets of data. One that directly the energy eigenvalues, and one of these periodic orbits. For the zeta function, you have the zeros of the Riemann zeta function, and you have the primes. And the possible suggestion is that in gravity, maybe the analogs of those things are the energy eigenvalues of the black hole and the fuzzball or microstate geometries. So there's another way that these fuzzball microstate geometries could be an interesting description of the system without them sort of directly representing the microstates themselves. Okay, that's it. Thanks.
Thank you, Douglas. So we move on to Emil, I suppose, and then we come back with questions. Okay, Emil, please.
All right. People seeing my screen? Hello?
Yes, we see the screen.
Yeah,
Okay.
it's fine. Got it.
Yeah, so I just had a list of questions that I periodically think about and always confuse me. Yeah, so one is how to connect the sorts of diagnostics that people talk about when they talk about chaos in the context of black holes, and some kind of bulk picture of microstates. So, in the calculations of Douglas and Stanford and Schenker, one's interested in computing the S matrix of gravitational shock waves near the black hole horizon. And so question is, what if you have a microstate geometry which has no horizon, what is supposed to reproduce that sort of picture? So do I need to consider a sufficiently generic ensemble of microstate geometries that they individually have some light cone structure, but the light cone structure is slightly different for each microstate? You know, and how well can a very complicated microstate geometry approximate chaos near the horizon? Now, for the reasons discussed by Ben, things are not very generic because we're near extremality, and so scrambling is slow. But the question is, a basic thrust of the question is, you know, the microstate geometries that we know how to construct are very coherent states. They're very far from typical. And so how far away from that paradigm do we need to get before we can start seeing some of the structure that one knows about in black hole physics? Another question is sort of what is it that's chaotic in the bulk description? And you know, one thing that maybe is a little bit more chaotic near the black hole horizon is that in situations where you don't have a horizon, then we're used to in GR considering diagnosing the geometry by thinking about congruences of null geodesics. And so is that, or do we have a situation where, you know, if you don't have a black hole, there's in some sense laminar flow of that congruence of geodesics, but that if you're sufficiently near the horizon of a black hole, that the tracers of the geometry, the null geodesics, start deviating from one another macroscopically as they flow along the horizon. That's certainly the picture that would be suggested, for instance, by the growth and decoherence of the fluctuations near the horizon that become Hawking radiation. And moving out more broadly, if gravity is an emergent phenomenon, as we're accustomed to in gauge gravity duality, is it in some sense all or nothing? So do we have to choose between an effective theory of gravity where there are gravitational degrees of freedom and the geometry is explicitly in our hands, or some microscopic description in terms of the gauge theory where you have the entropic degrees of freedom, but where figuring out where something is in the bulk is an extremely complicated and difficult question to answer? Or is there some third way? And this is, you know, the thrust of what I described in the last talk, where one has enough control over the bulk description and the microstates that we can begin piecing together a picture, including the microscopics of these phenomena like chaos and information scrambling and Hawking radiation. And the last question in this list I thought of is that related again to what Ben was saying, that scrambling slows down near extremality, that the temperature goes to zero, the entropy goes to the extremal entropy, and so the scrambling time gets very long. And so the question I would ask is that actually a simpler situation where, you know, we're thinking of black holes, you know, that are highly excited as just being complicated thermal systems where you know, over a scrambling time, the system executes some random unitary to go to some completely different part of the configuration space. But that slows down near extremality. And so this, in fact, might be a more well-behaved situation in which one can study in detail scrambling dynamics if one has enough of the phase space of microstates to scramble into. And here the question is one I posed at the end of my last talk of whether microstate geometries are sufficiently generic and whether indeed the scrambling dynamics that we see there is a scrambling dynamics into a very small set of special microstates, or whether it can teach us something about scrambling into the generic states that are available at a given energy above extremality. And of course, the thing one want to know then is, are there some universal features of that scrambling? How generic can one get using a bulk approach? And I think I'll stop there.
Okay, thanks, Emil. So the last speaker is Josif. Josif, are you? Yes.
Yes, let me share the screen. Okay. Can you see the screen?
Yes.
Okay, so it's just I just had a few comments and chaotic thoughts about correlators, and how can I link them to autocs. Maybe it's mainly my ignorance, but I think I hope people can help me. So we did this holographic calculation about a year ago with Ruben Monten and Pierre Heidmann and Nick about some solutions which are basically heavy states due to a superstratum, which is called the 1,0,n superstratum. And in this solution, if you look at the correlator and you ask how does the correlator compare to the BTZ one, to the one where in a black hole with an infinite throat, the answer is very similar. It's similar all the way to very, very long time. There's a tiny deviation at some point, but then you see a huge echo at times of order n1 times n1 times n5. And these times where you see the echo is actually the inverse of the mass gap. The inverse of the mass gap in this microstate geometries is given by the time when you see the echo. So in a sense, it looks like a deep ramp plateau kind of behavior. Of course, it's a BTC black hole. It's zero temperature on the right, finite temperature on the left. So it's a bit more complicated than your usual thermal decay in your usual black hole. But still, you see this very nice behavior. The microstate geometry is identical to the black hole behavior, with a tiny deviation in some intermediate regime, which is in green on the slide. And then at times of order n1 times n5, it actually becomes you actually get all the signal back. So one question which I had was, okay, this is a Lorentzian calculation, and essentially the heavy state is at -infinity and +infinity. Can one actually read off some autocs out of this? Can one actually compute the kind of correlators which you need in order to get the kind of correlators which Ben had on his slide, and which Douglas and Steve Schenker computed? Can one actually use this supersymmetric microstate geometries to compute anything of that sort? Can use this Lorentzian calculation for this purpose. Now, there's one thing about this mass gap, which is also very interesting. If you look at the CFT, at the dual of this microstate geometry, the CFT dual basically is made of ++ strands and 0,0 strands. This is just superstratum jargon. But the mass gap, which you compute at the orbifold point in the CFT, is of order 2 over the radius of the common D1D5 circle. So it's a very large mass gap. If you look at supergravity, and you go to the place where JR is equal to 1/2, which is basically the deepest possible throat, then you see that the mass gap in supergravity is much smaller. It's a factor of n1 times n5 smaller. And the question is this the mass gap one expects? Clearly, in the D1D5 system at weak coupling in the Higgs branch, you expect the mass gap, which is really 1 over n1 times n5. But Juan was saying in the discussion a few hours ago that no, you actually expect an exponential gap, and you can actually have in a supersymmetric system a gap which is actually which is even smaller. And that's the question that's one of the questions which I'm wondering about. We are matching very nicely from the supergravity this weakly coupled CFT mass gap for the longest possible strings. But the question is this what we expect, or maybe one should get even deeper, even smaller mass gaps? On the other hand, so there's a nice matching between typical microstates of the black hole and the superstrata for the mass gap, but the reflection on the other hand is not typical at all. You're getting all your signal back. The microstates spit out everything which you throw in, comes out perfectly. Now you can imagine more complicated solutions and more complicated plateaus and more complicated things, and this is a kind of thing which I would expect in a more unusual microstate geometry, which I can call H1 just for simplicity. You expect a similar return time, again over the 1/n times n5, a similar mass gap, but the scrambling, the system coming out is going to be much more different. It will not have the same height as the original signal. There will be some scrambling in this microstate, and the question is, can one actually, for example, estimate the height for these things? And the wild goose chase, which which I really dream of doing, but again, I don't know if it's possible, is to imagine some superposition of geometries. And this, I think, has to do with what Douglas was saying, because even if you have energy eigenstates which are not the coherent states, which are not classical geometries, you can imagine some quantum superposition of classical geometries which approximates very well an energy eigenstate and vice versa. So in principle, if I have, if I imagine some superposition of microstate geometries, the microstate geometries are colored, H1, H2, H3, H4, with some coefficient C1, C2, C4. But again, it's a sum over n1 times n5 over a huge number of geometries. One can compute very easily the guys which are H1 with light operators, H2 with light operators, and so on. But if you want to compute the 4-point function for the H, which is for the brown guy, which is again the quantum superposition, one needs to compute also a heavy light function where the two heavy functions are different. And there's a question, can one compute this thing in supergravity or not? Is there any way to compute this thing in supergravity? If one could find one, I mean, I think this would really be a nice calculation. And the other question is, okay, if I compute, let's say I compute this I compute this 4-point function in the superposition of geometries. Do you still expect to get a 1/n1 n5 gap, or do you expect to have a much smaller gap? And then that's again linked with the question which was asked before. Thanks.
Thank you, Yosif. Yeah, so I guess the floor is open for questions and discussion.
Maybe I have a comment about Yosif's for the last question. Just use the stringy Keldysh. The H1 and H2 are geometric, so there's no abstraction in doing it.
I don't know how to do it practically. So I mean, I know how to compute H1 light because I just take a microstate geometry dual to H1, and then I compute I compute a 2-point function in it. But to compute a 4-point function where the heavy guys are different, I need somehow to scatter. I need to move the heavy guys to another one.
You need to use the real-time dictionary.
It's a bit too cryptic, I think, for me.
Well, I mean, you need to use, so the real-time dictionary constructs a geometry corresponding to stringy Keldysh contour. So if you want to generate something which is between two states H1 and H2, which are both geometric, then you need a Euclidean piece for H1, then a Lorentzian piece, and another Lorentzian piece, and then return back to H2. And then to do the 2-point function, then you put boundary conditions in the Lorentzian piece. I mean, we did a lot of examples back in 2008.
But can you compute these Lorentzian and Euclidean things for this kind of superstrata geometries? I don't know how one goes to compute the Euclidean parts. I mean, Lorentzian, I'm very happy. I know how to do Lorentzian, but Euclidean, I just don't know what.
You just started saying you have a state H1, which is a heavy state, so that's a supergravity state. To generate this with in Euclidean particular, you already know what it is because you worked it out. Then you need to use the matching conditions. So.
Yeah, that's what I don't know technically, but again, that's a technical. I mean,
that's a technical question. Yeah, that's not. I thought the question was in,
it's doable. I mean,
in principle, all of this are computable.
Because I think we do have families of microstate geometries which Nick and Pierre have built, for example, which have different mass gaps, and in principle one could just take a superposition of those and compute, for example, what comes out. I mean, if one could do that, I mean that would be a nice calculation.
I mean, some fraction of these things are, if you want to describe what is a heavy state that's perturbatively nearby the state you started with, then you're interested in looking at the spectrum of supergravity modes that are bound states in the cap. And so there will be, in the S matrix, there will be, if you look at a 5-point function, right, where you have two heavy states at the beginning and the end, and you have a scattering state coming in, and the out state is an outgoing scattering state plus a bound state that's living in the cap. So that's the perturbative description of slightly deformed out states in the cap, which are slightly different heavy states.
Can I do this with a Witten diagram with 3 legs? In a microstate geometry background.
So I think you would, yes, I think you would calculate, you would just do an LSZ process, right? So you calculate the 3-point function in the microstate geometry, and you look for the LSZ poles for the 2 scattering states and the bound state.
Mm-hmm.
I have a question for Douglas. One was a trivial one and one perhaps less so. First, I just want to get a sense of, you mentioned this alternative formulation of billiards where you talked about Z smooth, and then you said that in microstate geometries, maybe that's the black hole. What is the Z smooth, or what is the contribution from the smooth thing in billiards?
Yeah, so that's like the contribution from an infinite billiards, but you just multiply it by the actual size of the stadium. So if for example, if you're working at quite high energies, then the billiards is very big compared to the wavelength of the particle. So then it's a good approximation to the thermodynamics to just take it to be an infinite billiard stadium, but then you rescale it by the volume.
So you were saying that these that maybe the microstate geometries don't actually represent the microstates themselves, and yet how do you reconcile that with the fact that we have a very precise holographic dictionary for some of these things? There are some microstates which we have very good evidence are exact duals of very particular states in the D1, D5 CFT.
Yeah, well, I guess those cases wouldn't be a good candidate for what I'm talking about. And I apologize for being a real outsider to this subject, and I don't really know if the idea is reasonable or not, but it's less that I'm...
For non-BPS, so what we're talking is that finite temperature non-BPS systems. I mean, what Nick is saying is about supersymmetric extremal microstates. So maybe that's
No, I'm sympathetic to the broader idea. I'm really wanting just to understand the intuition more deeply, so I can think about it in those terms.
Part of the intuition is, I feel that we're, from the perspective of quantum chaos, we're missing something in the bulk theory. We're missing the analog of the periodic orbits. And so we have the black holes solution that describes the thermodynamics, but if we want more detailed properties of the energy spectrum, then we would like to have an analog of this infinite sum over these periodic orbits. And one possibility that I first heard about from Steve Schenker is that maybe what we want is actually already kind of being studied in the literature in the context of fuzzballs or microstate geometry. It's like some additional set of classical solutions that are not the black hole. But so from this perspective, for example, you would not try to reproduce the entropy of the black hole by looking at these solutions. You would try to reproduce deviations from the exactly thermal prediction from these.
Can I ask a question on this? So these periodic orbits look like saddles of a high temperature expansion. Is this correct, right? Because you have beta in the denominator.
Yeah, so it's super convergent. It's very rapidly convergent at high temperature. That's right.
So in some
high temperature, yeah, sorry, go ahead.
The other extreme of the microstates, which seem to be very much tied to zero temperature. I mean, they are supersymmetric zero temperature solutions. And you seem to be looking for things that are dominating at very high temperature.
No, they're small at high temperature. So the contribution of the periodic orbits is small at high temperature.
Yes.
And it's big and important at low temperature. So maybe that would also be consistent.
Oh.
For relatively high temperatures, the solutions will have a serious time dependence in order for them to be periodic orbits. But at very low temperatures, they would have a very small time dependence, and then we could maybe they are well approximated by the static solutions that people are discussing now for BPS for BPS solutions.
Is this structure understood for anything other than simple dynamical systems where you have a few dynamical degrees of freedom? And it's like, is there a field theoretic analog of this sum over orbits? In some non-integrable field theory that has chaos?
I don't know. As far as I know, no. But I think also in more complicated chaotic systems like what you're asking about, we don't normally have even an analog of the first term. And I feel like in holography, we do have an analog at least of the first term. So then maybe we could hope to have an analogs of the higher terms as well. Like the smooth contribution. We have the black hole, right? For a typical chaotic many body system, we don't have some kind of useful way of computing the thermodynamics like the black hole solution. So we're at least kind of in the game in holography.
Mm-hmm.
Well,
I have a question for Douglas. Hi.
Hi.
Hello, hi. Douglas, the microstates of the SYK model are well known from the work of Maldacena and Kurkulu. And I was just wondering whether the partition function that you mentioned in the first slide can actually be organized in terms of those microstates. The second term, I mean, is there some idea how to do it?
That's interesting. I haven't really thought about it. It's true the partition function can be written as a sum over those things, but
yes.
I'm not sure they have the same interpretation. I'm not sure we should interpret those things as being the periodic orbits.
There may not be periodic orbits, but it would be generically, something that goes beyond the smooth semi-classical approximation, because these are very high energy states, as we know.
Well, they're high energy states, but you can make low energy versions of them by acting with the e to the minus beta h.
That's true. That's true.
Well, I don't know. I don't have a good answer to your question. I feel that those things are more analogous to just sort of directly the microstates using the boundary Hilbert space, not as analogous to the type of periodic orbits which we're looking for. But I don't know.
Okay, thank you.
I'd just like to make a comment that it is possible to construct quite explicit toy models of single particle probes of extremal black holes that do not show slow scrambling, but in fact show fast scrambling, and that in fact actually saturate the scrambling time bound. First, and second, that it is possible to show in these toy models how from a very non-smooth geometry that is in fact related to periodic orbits of these chaotic systems, it is possible to obtain in a suitable limit the smooth ADS2 near horizon ADS2 geometry. These are toy models, of course, but just to show that slow scrambling is not an inevitable feature of extremal black hole dynamics. It's just, it may occur, but there are examples where it need not occur, where fast scrambling can occur.
So Douglas, You seem to be suggesting, if your picture's right, that we've got the wrong end of the stick in the following sense, that we've been spending time trying to describe the thermodynamic behavior of black holes using microstates, whereas you're telling us that microstate geometries actually reflect some deviation from some standard thermodynamic model.
Yeah, that's exactly the flavor of the comments, but I'm not sure I would say that I'm telling you because I'm such an outsider to the subject. I'm just offering it as a possibility.
Oh, it's a really interesting thought. Mm.
I have a question for Josef and some of the, well, I'm not sure exactly who it's to, but Josef would be one example. In the bulk description of the Lyapunov exponent and the exponential growth of the out-of-time order correlator, this comes from some high relative boost of the different particles, and it depends, generating that large relative boost seems to depend on there being a horizon.
Extremal or non-extremal?
Well, in order to have a non-zero Lyapunov exponent, it should be non-extremal. And I feel like it's hard to imagine getting exponential growth like that in any kind of geometry that doesn't have a horizon. But I wondered if you could comment on that. Maybe it's naive.
I think the talk this morning by Jose Morales was showing that no, I mean, you know, even if you don't have a horizon, but you have this photon sphere, you can get some sort of behavior like that. You know, you have some geodesics which come in, some geodesics which go out, and there's a clean. I don't know if you saw the talk in the morning. I mean,
unfortunately, I think I was asleep then. But
so the point is, in the microstate geometries, one can compute a photon sphere, and then you have an incoming photon, and if it's slightly outside of the photon sphere, it gets deflected, and you know there's a nice fan of, like, you know, possible directions. If it's inside the photosphere, it gets absorbed, and that's something which you see in the black hole very easily. So at the photon sphere, but you don't see it at the horizon, you see it at the photon sphere. And then you can try to get a 4-point function using that kind of object. So instead of looking at something which comes in the horizon, you look at something at the photon sphere, and you can actually calculate the Lyapunov exponents using the photon sphere. And what they were finding is that for the microstate, for certain microstate geometries which have a long throat, the Lyapunov exponents of the photon sphere approach the Lyapunov exponents of the black hole quite a lot. So the microstate geometries approaches more and more and more. Essentially, you have you know, imagine having a BTZ black hole which has an ADS3 part, and then there's an ADS2 which goes on forever. In the microstate geometry, you just cap this ADS2 part, but you can cap it wherever you want. So you can make it deeper and deeper and deeper. And as you make it deeper and deeper and deeper, the Lyapunov exponent approaches more and more and more the non-trivial, the one you find in the black hole. Sorry, this is my rooster. I'm outside, so I guess Jose Morales is also.
Yes. No, I confirm your picture. The idea is that the physics near the photon sphere is very different from the one in the horizon. And it's not tied to the temperature of the black hole. It's tied to a different quantity, which is this Lyapunov exponent, which, by the way, governs also the damping of ring-down modes. I mean, it's a very interesting quantity. And as Josef was saying, it's a very simple computation. Just at the classical level, classical gravity, you can compute the lambda by simply computing the exponential deviation of nearby trajectories. And you find a lambda that is always below the bound that you establish, except for a very tiny region near extremality. It's exactly this point near extremality where the temperature is 0. Instead, this Lyapunov exponent is not 0. And for all this supersymmetric solution, you find a finite result. And okay, of course, we should understand what is happening in this tiny region near extremality. This is very interesting. We still don't understand. But it's very funny that this, for let's say 99% of the modular space, this Lyapunov exponent is below the bound of 2 pi t. It's below minus 2 pi t. Let's stress again, the temperature is not, the temperature govern the Lyapunov exponent near the horizon, but near the photon sphere, there is a different quantity.
I think this Lyapunov exponent, so that sounds like an interesting calculation. I don't think it's the same type of thing as the out-of-time order correlator, Lyapunov exponent.
No, this Lyapunov exponent is defined as like exponential deviation of nearby trajectories. This is a classical
Yeah,
case.
it's for like a single free particle moving in the background. It's not
Exactly.
Governing the gravitational interaction of two different particles.
But you can map in holography if you are in ADS background. In ADS background, this scattering process near the photosphere, you can map again to out of time of order in principle correlator. Then we believe that this will be a signal, you will find a signal for this particular case. It's very, I insist, it's a very strange situation where the photosphere is crashing against the horizon. It's a very tiny region near the extremality. Therefore, away from extremality, this lambda is always below 2 pi t, but near the extremal, nothing happened to this lambda. It's not going to zero, nothing happened, while the lambda of the Lyapunov is falling near the horizon is falling to zero. Okay, of course. Okay, this is this relation between Lyapunov exponent of nearby geodesics and Ringland-Moser was found more than 10 years ago by Cardoso and collaborators. But when we were inspired by your work and we were trying to see how this whether this lambda was respect your bound and so on, and we find that almost always is the case, but not near extremality. Therefore, something funny happened near extremality. And I think it's something we should think more about it. And it would be also nice to see the picture. But okay, the picture is very clear. You have ADS background, and you do a scattering near the photosphere. And there is a chaotic behavior of these geodesics, and you ask what happened in the boundary CFT. What is the dual of this scattering process in the boundary CFT?
You said something in there just a moment ago where you suggested that we're not seeing the right Lyapunov exponent if we're looking at just single particles probing the geometry. We should be looking at something which involves the gravitational interaction of two particles. Can you just expand on that thought? Is probing with a single geodesic or a single wave never going to see the Lyapunov exponent we need to see?
Well, that will never see this many-body quantum Lyapunov exponent that's the 2 pi over beta for black holes. That one comes from taking two different particles on the black hole geometry and studying their scattering. And their scattering gets enhanced because they're highly boosted relative to each other. And the reason they're highly boosted relative to each other is connected to the existence of a horizon in the geometry.
Yes, but
so the replacement.
Go
ahead.
Kostas, you're the traffic cop.
Yes, whoever speaks louder, I guess, has the floor.
No, let me comment on this point. The photon sphere is very similar to the horizon in this sense. In the scattering near the horizon, you use the fact that the horizon has a Ringler structure, and this fits that this Lyapunov exponent is always 2 pi times the temperature. The photon sphere is very similar because the photon sphere also looks like a horizon, just that is a horizon for very specific choice of the impact parameters. But the physics, again, you have a logarithmic diverging time delay and so on. It's very similar to the horizon. It's just that it's tied to a different sort of temperature.
But I think, Jose, the question, I think, is that you need two particles in this geometry to see the analog of the OTOC, right? And you only have one.
If I may add something to the discussion, if you scattering particles near the horizon, it has a nice picture with back reaction that Hoft had looked at in the past. And it corresponds to the Hamiltonian of an accelerated observer in the near horizon region. So an observer that reaches infinity. And if you write how information about an ingoing particle gets mapped to information to an outgoing particle of the outgoing Hawking quanta, they're related by a Fourier transform if you do the scatter, if you look at how a Hoft looks at it. So this is related to the spectrum of the dilation operator, which is the Hamiltonian of the observer that's going to infinity. this looks like an inverted harmonic oscillator, so it's unbounded from below. But if you demand that, or if you look at the symmetries of this operator, it has a very special point, which is the bifurcation sphere. And if you demand that you cannot go arbitrarily close to the bifurcation sphere, but you look at something that fixes a Planckian distance away from the horizon, then this discretizes the spectrum, and it gives something that's very similar to the Berry-Keating Hamiltonian. And the spectrum seems to be picked out. The spectrum seems to capture exactly the Riemann zeros that Douglas was talking about. So these are energy eigenstates of the Hamiltonian of the dilation operator of the observer that reaches infinity. And in the near horizon region, so this is between the photon sphere that Jose was talking about and the horizon. I'm not sure how this spectrum relates to the microstate geometries, but these are energy eigenstates of this observer, and they seem to be related to the zeros of the Riemann zeta function.
So in the microstate geometries that have been constructed, the replacement for the horizon is in some ways the gravitational wave that's running around the cap, the ADS3 cap. So you have this ADS3 region, then you have something that looks like a BTZ throat, and then it caps off in some smooth ADS region. But the thing that stabilizes it is that there's a gravitational wave running around in the bottom. So there is a large relative boost if you send a probe in, which is that probe can undergo, which is what is essentially a gravitational shock wave collision with the supergravity modes that are already sitting there in the cap, which are giving you the momentum, which is the third charge in the solution. So I don't know, the analog of an OTOC might have to do with how that probe interacts as a sort of a gravitational shock wave scattering. Because if you drop something from the top of the throat, by the time it gets down to the bottom where the source of the superstratum is, it's highly boosted.
I think the analogy will be that one quantum falls into this long throat, and another quantum will come out of it and will then go to the boundary, and where they meet will be the analog of the scattering process. It won't be at the horizon. It will be so the Lyapunov growth, or the slow version of it, will be capped because the throat is not infinitely long. But I think the mechanism will be very similar. It won't be exponential in these cases because it is slow scrambling, but I do think you will have this OTOC that will grow like a power law, and it will come from one quantum falling into this throat, another one coming out, and they will meet somewhere and interact.
But there's a question about the slow scrambling. If you have a particle, if the black hole has right moving momentum and the particle which you throw in has left moving momentum, from the perspective of the left moving particle, it's feeling a temperature. I mean, if you look at the 2-point function in this microstate geometry, it's decaying exactly like BTZ. There's a nice exponential decay with the right moving temperature. So there are many particles that you can throw, which essentially, even if this black hole is supersymmetric and so on, I mean, it has a non-trivial right moving temperature, which is fed by a huge amount of particles. So those particles should have fast scrambling. You know, they are just going against. So you have the microstate modes going one way, and you have the particle going the other way. They're going to scatter exactly like this, like they scatter in a non-supersymmetric black hole.
I think part of the reason why we haven't seen this in microstate geometries is, in fact, because to make the computations, we've actually washed out an awful lot of the things that will actually produce this kind of phenomenon. So, for example, we've coiffured the hell out of single modes so that the geometry doesn't have too many bumps in it, because if it's got bumps in it, it's very hard to analyze. But in fact, a generic microstate geometry is going to have a sort of washboard, incredibly complex, bumpy structure. And when you fit a particle into that, particularly since it's that bumpy structure is going to be some left moving wave, it's going to scatter in just all sorts of different directions generically and have very divergent growth on divergent geodesics based on neighboring geodesics, very strong tidal forces. The things we can analyze have all that kind of structure washed out so that we can analyze them. And in fact, we should be doing the opposite, I think.
Well, it is possible to make some toy models that do exactly illustrate what Josef was mentioning before. Therefore, that if one does have a single particle, but in a non-smooth geometry made by the microstates of an extremal black hole, then it is possible to show that the scrambling, first of all, will be fast, and it, in fact, will saturate the scrambling time bound. So it is not inevitable that slow scrambling is a property of extremal black hole geometry.
But the question
could you say that again?
Josef, can I just, you said something about the, you said that in your example that you saw, the decay of the 2-point function in BTZ was exponential, but I thought if you tracked, like, because of these images, I thought it was still a power law decay.
No, so it's actually double. I mean, I don't know if you saw. I mean, okay, I can share again my I can share again the screen. Just 1 second. Let me get, where is it? Put it somewhere and it vanished.
But sorry, while you're looking at that, maybe I can just make a comment, which is that I think in these geometries, if you want to know what the growth is gonna of the computer squared is gonna be, it comes down to some calculation of asking how long does the probe take to fall in, and how redshifted does it get.
So here's the so if you look at the curve here with the BTZ region, the red curve is the BTZ black hole and the blue curve is the microstate. So you see that for a huge amount of time, you get exactly the same responses in BTZ. And this interpolation of peaks and stuff, this is exactly the fact that you have right movers, which are, so it's a periodic thing, and the right movers are exponentially suppressed and the left movers are power law suppressed. So you get exactly the same feature. It looks like BTZ, quacks like BTZ, walks like BTZ, it's all BTZ. And then you really have to wait for a huge amount of time. And then at some point, you know, the particle goes down the throat, hits the structure, the wave, and then comes out. And then you see the wave coming out in its all full glory in this side. That's basically what happens. So the fall down and the collapse into the black hole is exactly like in BTZ. You cannot see any difference. So for short times, it looks like perfect BTZ. You don't see anything. You don't see any structure. It's only if you wait a time which is over the n1 times n5 that you see structure. And this time is the inverse of the mass gap. So again, when you have a microstate which has a mass gap 1 over n1 and 5, the time it takes for you to come back is n1 times n5. So it is falling into the thing. I mean, it's very similar to BTZ. Again, the two graphs are superposed. You don't even see them. They are hard to see on top of each other. So there's the red one and
the question wasn't about the difference between BTZ and your geometry. I was commenting that I thought that if you look at observables in BTZ, in this extremal BTZ, they still decayed with power law tails rather than exponential.
No, there are two: right movers and left movers. Right movers decay power law and exponential, and left movers decay power law.
But if you compute it, yeah.
This is just the typical BTZ result.
Ben.
But as if you do the computation for the OTOC, these behaviors of left and right movers will alternate in the result, and on average it will go like the power law decay.
Can one find some OTOC? Can one find some other OTOC where one can capture this exponential behavior of BTZ? There must be some other type of OTOC. I mean, I'm sure that. I mean,
well, you can capture it. Right? You can capture it, you can isolate it, but it's for small amounts of time. I mean, I think you have a number of e-faults, so you can display it, but it will not be something that grows for a long time at this rate. It will be some little move on top of the power law growth that you have based on the zero temperature. That's in this paper of Sharoshi and Mazei that I was mentioning.
Okay, that would be interesting to figure out, because I mean, in principle,
they didn't do it for the zero. They didn't do it for the power law. They were not looking at the extremal case, but I think if you extrapolate it to the extremal case, it should be that you get power law growth, and on top of that, this sawtooth profile. That's what I'm expecting.
Is the sawtooth profile the kind of stuff we get here? Because, for example, if you look at our solution, again, the solution comes out from the throat, but then if you look at the time, which is 2 n1 and 5, so then it decays again, and it comes out again, and then decays again, comes out again. So it actually goes, so every n1 and 5 interval, the signal comes back, and then collapses again, and then comes back again and collapses again. This is the behavior. It's a very special microstate. Again, it's this 1, 0, in superstratum. It's not a typical one, but somehow the system comes up again and back and up and back. I don't know if this sawtooth is a similar thing, or is it rather the sawtooth something similar to what you see at the beginning of the BTZ region?
No, that's it's different from what you have, because the period of that would be the time to go around the horizon.
Ah, but then this
so
is
that's not very fast. That's why it's very small as well.
I see. But then this is exactly this BTZ. This is the sawtooth that you see in BTZ.
Okay, right. So overall, it's power law, but you do have some.
Yeah, you have these bumps. Indeed.
Mm-hmm.
So just another thing, Daniel in his talk mentioned what we're trying to converge on at the moment, which is we think we can begin to do things that are near near extremal. So in fact, we think we know how to scatter a left moving momentum wave against a right moving momentum wave, at least set it up numerically so that we can watch them collide as they go down the bottom of a hole. And presumably when they collide, they'll emit some gravitational radiation. So if one can construct such a, I guess I'll ask Ben, if one could actually construct a solution, albeit numerically, what would be the thing to look for if I was going to try and detect chaos in such a solution? So this would be a left-moving momentum wave on a D1, D5 system passing through a right-moving momentum wave at speed of light, and they're bouncing against each other, emitting gravitational waves. What should I look for if I really wanted to look for chaos in that process?
I think the easiest way is you need the geodesics in that background. So you have some geodesic that comes in from the boundary from the past. You have one that moves back from the future. So if you can compute those and then see how they locally scatter close to the would-be horizon, that would give you the Lyapunov growth or the slow analog of it.
But I can make that kind of behavior already in just in BPS things. I can imagine making a very complicated BPS state with all sorts of crap and complicated structure in the cap. We tended to wash it out up until now, but I could make something with an elephant in the middle. I could send stuff in and it would scatter like crazy.
Yeah, absolutely. So that's.
Could I make a comment?
I think
about
this computation can be done at the 0 temperature one. You will not find the exponential growth for a long time, but you can find the power law growth, I believe. If you do want proper Lyapunov growth for a long time, you will need to get to near extremal so that you can wait long enough and get a proper exponential. But conceptually, I believe that it's already present there without the exponential growth.
Sorry, Douglas, you were going to say
Yes.
Yeah, I just wanted to say that with respect to putting this crap on the elephants and so on, that can help you with getting decay of the 2-point function, but it doesn't help you get exponential growth of the out-of-time order 4-point function.
Okay.
Can I have a related question to the chaotic people out there? So if I want to study chaos in any classical geometry, is it enough to study the propagation of one field in that geometry, say a scalar field, but just study it holographically? I mean, there's the real-time holography is a way that you can compute from the book perspective many point functions in principle. So is it enough to just put one scalar, say in my background, and just let it propagate and study 4-point function? Is that enough to probe chaos, or I need something more?
Well, you need to have, depends what aspect of chaos you're trying to probe. But if you're interested in this butterfly effect, kind of the Eikonal exponent deal, then you need to include gravitational interaction of that field. So you would consider, it's fine to have just one field in the bulk, a phi, but you need to set up a scattering problem with 2 different quanta of the field phi, and they need to interact with each other gravitationally. Normally, such gravitational interactions are small, like they're proportional to G newtons, so for many purposes we ignore them. But the reason why they become important in this out-of-time order correlator is that the 2 different quanta are highly boosted relative to each other. So the gravitational interactions become large.
So it's not enough to have a minimally coupled scalar without like 5 to the 4th term or something like that, where
No, the 5 to the
scalar
4th term
self
doesn't
interacts.
matter. It's the fact that the metric is coupled to the scalar field. So you can have a scalar field with a quadratic action, but it's coupled to the metric, like through the g mu nu, d mu phi, d nu phi. And that's enough. That generates the interaction that you need. That's like a 3-point interaction between 2 phis and 1 graviton.
But then I would need some sort of like, even if it's tiny, back reaction, because like, for example, in Pierre's talk, we saw a study of like scalar field propagating in a microstate background, but it was fully like back reaction was fully ignored. It was just like this, the background, no coupling, just scalar propagates there. Or am I getting it wrong? So like, should I do something, if I want to study chaos in a fuzzball background, should I study something different than propagating waves?
Well, propagating waves is part of it, but you also need to include scattering of those propagating waves through gravitational interactions.
Okay.
And I think a shorthand for how to do it, to see whether you're going to get the right effect, is to just follow 2 particles, that one falls in at time 0, another is sent in backwards in time from time t, and they approach each other like this, and you can ask about their relative boost. And if the relative boost is growing exponentially in time, then you're going to have a positive Lyapunov exponent. And if the relative boost is not growing exponentially in time, then I think you probably will not have a positive Lyapunov exponent.
But that's a 6-point function, because the microstate, the fuzzball is already it's already in a heavy state. So you have a heavy state, and you want to compute the thing in a you want to basically compute a 6-point function in the CFT.
Right.
You have
Well, yes, but it's the bulk calculation is not so bad. Like, we're not trying to compute it in the CFT, I guess, in this discussion. Well, I don't know. Maybe we are.
Can I just clarify on a point that Emil was making earlier? In the microstate geometry, we really do have a fully back-reacted scalar excitation, in a sense, in the gravitational background. It's purely left moving. That's what makes it BPS. So if one sent it, is there any way you could just send in another scalar probe so that it scatters off that fully back-reacted scalar wave?
I don't think that's going to help. That scalar wave or whatever, I understand that's part of the background, right? That's part of the original state.
Right.
So in addition to that state, you need to have 4 new operators, creation and annihilation operators for 2 different quanta. Those 2 quanta need to interact with each other.
Sorry, Douglas, could you consider a 4-point function make of 2 heavy states? And they say the macrostates is one heavy state coming, and the other is the light states. It's a 4-point function, but you have 2 heavy states and 2 light states.
Yeah, that I think is computing basically the 2-point function in this background. So it's, for that, you just need to study the propagation of a particle in the background, but it doesn't tell you about many-body chaos.
Yeah,
well, it can tell you about the exponential decay of that 2-point function, which is an interesting thing, but it's not the butterfly effect.
But the question is, in principle, a 4-point function can tell you about this butterfly effect. The question is, can you massage the 4-point function and compute holographically with heavy light into something from which you can get the butterfly effect?
I don't think so, no.
Okay, but
it's a 4-point function in a black hole background.
Sorry?
A 4-point function in a thermal background would do, but so that's like a 6-point function with 2 heavy states and 4 light ones. But Douglas, wouldn't you agree that if you're happy to find exponential behavior for some large but finite time, that you don't need like the last slice of space near the horizon? So if you kept off, say, a Schwarzschild geometry like extremely close to horizon, you would still get some transient Lyapunov growth for as long as you want, as long as the region that you kept off is sufficiently small.
Well, how does it compare to G Newton?
Well, it will be small, so you need to take, well, I guess you need to tell me how long you want the exponential behavior to last for. So,
well, the thing is that it needs to last for an amount of time that grows as G Newton becomes small.
Exactly. So the slice that I can cut away will be like will be tiny on a scale of G Newton.
Okay.
But if they can make a microstate that only cuts away like a tiny slice right outside the horizon, I think you're fine if you're happy with some, and you only get some finite time of Lyapunov growth anyway, because there's a quasi-normal mode decay that will kick in at some point?
Yeah, I'm not sure. I'm not sure if I don't want to commit to being happy in that situation, but I might be. Like the kind of thing I might worry about is what if I send in some very low energy particle or something? Then the scrambling time gets delayed. It gets longer, but it still scrambles. It just takes longer.
But
And
it's
so
low
then
energy
it would.
with respect to infinity. If you're sending something that's low energy with respect to you at infinity.
By low energy, I mean low P plus.
Enormously.
So, I mean low P plus. So that thing grows exponentially, but if it starts out very small, then we need it to grow for a very large amount, and so we need the slice to be even closer to the horizon. So I'm just not
going to get blue shifted enormously when it's getting.
Well, yeah, but what Ben is saying is it'll get blue shifted by an enormous but finite amount, and I'm worried that in that case we could potentially set up some kind of a probe that would need an even larger blue shift to make it significant.
Absolutely. For any specific OTOC, you could arrange it that you will get as much exponential growth as you want. But indeed, if you then take other operators or something, then it might not be enough. I agree. I would agree with that.
Let me ask a naive question. Is the scrambling related? So how is the behavior of and the Lyapunov growth of the OTOC related to scrambling? Do I need to have the exponential density of states of the black hole in order to match the right Lyapunov exponent to the OTOC? Or if I just have a limited set of microstates, should I be expecting to see Lyapunov growth with almost the right exponent?
You're asking whether you need lots of states in order to get the exponential growth?
Yeah, with the right exponent.
I think you need a lot of states because
if I had not, the full BTZ entropy worth of states, but I had, some tiny fraction of them, maybe, 1/1000th of the entropy, would I expect the Lyapunov exponent to be 1/1000th of the maximum one?
No, I don't think so. I think that, well, you need a lot of states in order to get exponential decay or exponential growth in correlation functions as a function of time. If you have a small amount of states, you just get oscillations. So you need a very large number of states to mock up these kinds of exponential functions. But in the situation you're describing, you would have a very large number of states. So I don't think that by itself is an obstruction.
But what's relevant would be whether the Lyapunov exponent computed that way would saturate your bound, because you could imagine that if you had very few states or you had capped the states, you would get a Lyapunov exponent, but it would not necessarily be sensitive to the fact that it has a lower bound that is very particular. There are two issues here. One is the Lyapunov exponent itself, and the other is in what way, whether the Lyapunov exponent computed that way saturates this lower bound or not. I mean, I think that for the black holes, that's the interesting part, that for a black hole, the Lyapunov exponent cannot be as low as you want. It has a lower bound.
Maybe I didn't understand where we were putting the reduced number of states. Like the 4-point function has some sum over states in various places if we write it out in terms of matrix elements. Are we supposed to just truncate all of those sums to some subset of the states, or what did you have in mind, Emil?
So I had in mind the fact that I don't think we're expecting microstate geometries to capture all of the entropy. There are various estimates, like for instance, Masaki Shigemori did some rough estimate of how many states you expect to be able to get from this sort of a construction. And it's, for instance, I think his calculation was that it had Q to the 5/4 growth instead of Q to the 3/2. So if I'm in a situation like that, where I'm badly missing the majority of the entropy, what would you expect the OTOC to look like?
I see. Maybe in a situation like that,
just by hand, I say, okay, I'm going to restrict myself to processes which only involve this subset of states. What should I expect?
Well, I think it depends on the subset of states. If they're typical states, it's fine. But if they're very atypical states, then I don't know. Depends on how they're atypical.
Maybe we should be asking the organizers. I mean, we are now getting over time. I'm happy to stay on and continue, but Nick, Yosif, what is the...
You know, I'm happy to continue for another 10 minutes or so, shall we?
So we never have an upper bound. Saclay seminars and talks never have an upper bound. It's always a soft upper bound.
But I think we should aim to sort of wrap it up in 10 minutes.
Okay, so we continue, yeah, please.
Sorry, Emil, I was confused about the premise of your question because in the, we don't really need to know all of the microstates of the black hole in order to do the gravity version of the calculation of the OTOC, right? You can just do it for a Schwarzschild black hole or something where you don't know any of the microstates. So if you give a particular microstate, you could compute in that geometric background, a particular OTOC. And you might wonder whether it reproduces the typical behavior of the black hole, but I don't see that there's like some sum over geometries you need to include or something.
Well, there are ways in which the geometries that have been constructed so far differ substantially from the BTZ geometry. They have rather substantial tails in the metric coefficients that mean that they differ from the BTZ geometry in important ways, even relatively far up the throat. And so, you know, if I had a collection of such states which didn't have a very large tail, and I could convince myself that that the scattering, you know, stayed within that collection of states, then maybe, you know, I think this is the sort of the hope that Nick and Yosef have had, and they can correct me if I'm misrepresenting them, is that the states are sufficiently generic that a calculation you would do in those states would accurately mimic most of the properties that you would expect a black hole to have. And I guess the worry I'm expressing is that from what I was presenting a little earlier, it seems like that they're very specially constructed states, and most of the phase space is somewhere else. And if most of the phase space is somewhere else, then you could worry that the lamppost I'm looking under is going to miss important properties. And so I was wondering whether the scrambling and the OTOC would be one of those properties.
Right, I mean, as far as I understand the calculation, at least to 0th order, the important features of the microstate is how long does it take to fall down the throat, and what is the redshift at the bottom of the throat, right? And I think in these superstrata geometries, as long as you take A small enough, you can arbitrarily get close to BTZ in those two important respects.
Yeah, there's in principle like no obstruction to computing. Try to compute OTOX in a single microstate and see what happens. I think this is going to be a very good thing to do. But I had a comment about something that Yosif was saying, and Emil is actually looking for, like averages over geometry. So Yosif was asking about a toy model where you can see like a linear superposition of heavy states, and you send a propagation in this linear superposition. So by the way, I'm Vasco Dimitrov. I work with Bert on the things that he talked in the first talk. And so in our wormhole toy model, it is very far away and misses a lot of the structure that superstrata microstates have. But the feature there, like a bug, you can turn it into a feature always, is that you have one parameter. And in fact, in a paper that it's supposed to come very soon, probably even this week, we do this averaging over this parameter lambda. And we indeed see suppression of echoes. So like just, and of course there is, because this parameter one, we have no idea what, like it's a toy model, we don't have any physical idea of what say distribution we should take. But we just tested that for various different things that we can do with this parameter, which effectively controls only the length of the throat. You get suppression of echoes. So this is just a very preliminary result that, in a way, it's easy if you had all the states, it's very easy to average over them.
What I had in mind was mainly computing it for multiple superstrata where the wave equation is separable and then summing them up. But again, I need to understand how Costas was. I mean, again, what you need to compute is a heavy guy with light and another heavy guy. And, that's something which, I need to understand how Costas's Euclidean thing works in order to try to implement that.
Sorry, which weight do you use to average the states? To compute this average?
I just want to put a random. I want to put a random configuration. I just want to put random numbers and average over I have a family of superstrata and I just want to put some random numbers. The main question is if you look at the quantum superposition of microstates, do you get the mass gap which is 1 over n1 and 5? Do you get the signal to come out of the grave after time which is n1 and 5, or can you actually get much longer times? That's.
Yeah, so exactly with this very crude model that we did with random sampling of these lambda values, we can indeed get the coming out of the grave, we can get it to be way higher than the one from any single one of these. And in particular, if you take a random distribution of lambdas, you get exactly e to the s recurrence, which is this which is reminiscent to these Poincare recurrences. So indeed, so if you pick your parameters to be some equally spaced, say, the recurrence doesn't it's also early, order n1 and 5. But if you take them randomly, then basically you have this huge phase space which is a torus, in complex frequencies. And if you take the parameters being completely arbitrary, they can only constructively interfere again after a very doubly exponential time. So this effect we see, but again, it's not our model is not it's not rich enough to capture all the physics that.
It's not the constructive interference that is the feature; it's the destructive interference. You want if this is really a superposition and not not an averaging, you would have not only constructive interference but destructive interference.
Oh, right.
So destructive interference that is missing when you do the same kind of average.
Right. So there is destructive interference initially. Actually, for a very, very long time, there is destructive interference, but as in the same way that in just generic QFT and you have Poincare recurrences on compact, put to QFT in compact space. You have Poincare recurrences after time, which is e to the s. So this is just what I call constructive probability.
Okay, but then you need something to impose the compactness.
Yes.
In order to get that in the back.
Yes.
Otherwise, it will just disperse.
Yes, exactly. Yes.
I was trying to think of a way to put flesh on Emil's question, and along the lines of calculations we might, if life is good, be able to do. And so one of the things that we know is in the D1, D5 system, we have all the index states, which are some very complicated combination of twisted sector states, which move left movers and right movers. And so the generic chaotic behavior is when left movers and right movers on the D1, D5 system collide with each other, produce gravitons, closed string modes, and all that sort of stuff. And that's where you should, of course, see this behavior of the OTOC. Suppose you couldn't do that. Suppose you could only, say, do the left moving and right moving modes with the alpha -1 oscillators, or just some, all the possible excitations, but with only one class of oscillators. Would you still see the correct behavior of the OTOC out of that, or would you?
You would if you had a way to make them come back after some time. If they just had this. They just interacted and then just flew off.
No, they're going around in a circle.
If they are going around in circles and they do come back, then indeed, yes, indeed, you would have them.
Even if you're taking a very limited subset of all the possible oscillator excitations you could make on the D1, D5
yes,
system.
because if that's because you would get that behavior within that subset. You would get the typical behavior of the OTOC within that subset.
Okay.
you would saturate the bound, you'd be sent to the lower bound of that subset, of the temperature that's determined by that subset itself.
So I'd have to probe it with the right probe.
That's right.
Right. So some fatigue setting in, I think. So maybe is this a good time to
I think so.
open way we continue tomorrow, I guess. So
just a reminder, we continue at 14:30 tomorrow.
All right. So let's thank very much the 4 speakers and everyone else participating in the discussion, and see you all tomorrow then.